66 million years ago, a giant rock from space changed the history of our planet forever. What seemed like just an ordinary day for the dinosaurs became the end of an entire era. Today, we look at the sky and see thousands of asteroids traveling in the darkness. Scientists try to create a shield to protect us, but they found out that this is much harder than what we see in action movies. This forces us to ask a very important question about our future. Are we really ready to face the forces of the universe? Get ready to sleep while listening to this video. Subscribe to the channel. Leave your like and comment from which part of the world you are watching. Settle in and relax. Let's start. Imagine trying to spot a single dot, dim speck of dust in an endless, dark cathedral that spans millions of miles. That is the sheer scale of the challenge we face when it comes to detecting asteroids that could pose a threat to Earth. The very first step in protecting our planet is knowing what is out there, and that is far easier said than done. Our current telescope technology, while advanced, has some glaring limitations that make this task incredibly difficult. One of the biggest issues is the blind spot created by the sun. Because of the intense glare, telescopes cannot see anything approaching from that direction, meaning an asteroid could be heading straight for us without any warning until it is too late. Most near-Earth objects are not large and bright. They are often small, dark, and reflect very little light, making them nearly invisible against the blackness of space until they are relatively close. Detecting these objects requires them to be within a certain range, and even then, we need highly sensitive equipment and perfect conditions. The smaller the asteroid, the harder it is to detect. But even a small one can cause significant damage if it strikes a populated area. For instance, the Chelyabinsk meteor, which was about 20 meters in diameter, went undetected until it entered the atmosphere because it came from the direction of the sun. That event injured over 1,000 people and caused widespread property damage, highlighting the urgent need for improved detection capabilities to effectively defend against such threats. We need years, ideally decades, of advance warning. This allows time to track the object, confirm its trajectory, and if necessary, plan and execute a deflection mission. However, achieving that level of warning is a monumental task. Projects like NASA's Near-Earth Object Surveyor, or NEO Surveyor, DOT, aim to address these gaps by using infrared sensors to detect the heat emitted by asteroids, since even dark objects radiate heat. This method can reveal those that are invisible in optical light, but such initiatives depend heavily on consistent funding and technological success, both of which are uncertain. Without a nearly complete catalogue of all potentially hazardous objects, any asteroid defence system would be useless because we would not know what to defend against. The sheer number of objects involved is staggering. Estimates suggest there are millions of near-Earth asteroids, and monitoring them requires scanning an almost infinite volume of space. Current ground-based surveys, like the Catalina Sky Survey and Pan-STARRS, have discovered thousands of asteroids, but many more remain undetected. These surveys use wide-field telescopes that take multiple images of the sky each night, and software then identifies moving objects by comparing these images. This process is akin to finding a moving car in a series of time-lapse photographs, but it is complicated by false positives from stars, satellites, and cosmic rays. Each potential detection must be verified through follow-up observations, which consumes time and resources. Moreover, observational constraints such as weather, moonlight, and atmospheric turbulence limit how much can be seen from Earth. Space-based telescopes avoid some of these issues, but they are more expensive to build, launch, and maintain. For example, The upcoming NEO Surveyor will orbit at a Lagrange point, providing a stable platform for continuous observation without atmospheric interference. Its infrared capabilities are crucial because many asteroids are carbonaceous, meaning they are composed of dark materials that absorb light and are exceptionally hard to spot in visible wavelengths. Others are metallic or stony, but regardless of composition, their low albedo makes them challenging to detect. The importance of early detection cannot be overstated. With sufficient lead time, even a small velocity change can deflect an asteroid enough to miss Earth. But without that early warning, our options diminish rapidly. The problem is exacerbated by the dynamic nature of asteroid orbits. Gravitational perturbations from planets, especially Jupiter, can alter an asteroid's path over time, turning a once harmless object into a potential threat. Additionally, the Yarkovsky effect, where an asteroid's rotation causes it to emit thermal radiation unevenly, acts like a tiny thruster, slowly changing its trajectory over decades. This means that continuous monitoring is essential not only for discovering new asteroids, but also for updating the orbits of known ones. International collaboration is vital in this effort because no single country can monitor the entire sky. Organizations like the International Astronomical Union's Minor Planet Center facilitate data sharing among observatories worldwide, pooling resources to improve detection rates. However, coordination involves logistical and political challenges, including funding disparities and data ownership issues. The psychological aspect also plays a role, because large impacts are rare events occurring on million-year timescales. It is easy for governments and the public to become complacent. This leads to underfunding and a lack of sustained commitment. Yet, the consequences of a missed detection could be catastrophic, as evidenced by historical impact events that caused mass extinctions. Therefore, treating asteroid detection as a global insurance policy is prudent. The cost of developing and maintaining detection networks is significant, but it pales in comparison to the potential damage from an impact, which could run into trillions of dollars and result in immense loss of life. Advancing technology offers hope. Machine learning algorithms are being integrated into survey data processing to identify asteroids more efficiently and reduce false positives. Citizen science projects also contribute, with amateurs sometimes spotting objects missed by professional surveys. But technology alone is not enough. We need a long-term, stable funding stream and international agreements to ensure continuous operation of detection systems. The role of public awareness and education cannot be ignored. When people understand the risk, they are more likely to support funding initiatives. NASA's Planetary Defense Coordination Office works to raise awareness and coordinate efforts, but broader engagement is necessary. Another challenge is the detection of fast-moving objects, such as interstellar asteroids like Oumuamua, which pass through our solar system at high velocities and from unpredictable directions. Our current surveys are optimized for objects within the solar system, so these interstellar visitors can slip through undetected until they are already departing. Enhancing our detection capabilities to cover such threats requires even more advanced technology and international cooperation. In summary, the detection problem is the cornerstone of planetary defense. Without accurate, timely detection, all other measures, deflection, destruction, or evacuation, are futile. We have the technological knowledge to build better systems, but what we lack is the unwavering commitment and resources to see it through. The quest to find that cosmic needle in the haystack is one of the most critical endeavours humanity can undertake, for it safeguards our very existence. As we look to the future, we must prioritise this effort, ensuring that we leave no stone unturned, quite literally. in our search for celestial threats. The journey is daunting, but with persistence and collaboration, we can overcome the challenges and protect our planet for generations to come. Remember, the universe is vast, and the threats are real, but our ability to detect them is the first line of defense. Let us not wait for a wake-up call like Chelyabinsk to remind us of the importance of this mission. Instead, let us act now, with vigilance and determination, to secure a safer future. The tools are at our disposal. We need only to use them effectively. From ground-based observatories to space telescopes, every addition to our detection network brings us closer to a comprehensive understanding of the near-Earth environment. And with each new asteroid catalogued, we reduce the uncertainty and increase our preparedness. So, while the task may seem overwhelming, progress is being made, and every step forward counts. The key is to maintain momentum and avoid the pitfalls of complacency. By working together across borders and disciplines, we can turn the impossible into the achievable and ensure that Earth remains a safe haven in the cosmos. So, we have this massive catalogue of asteroids, thanks to our detection efforts. But knowing where something is right now is only half the battle. The real trick is predicting where it will be years or even decades from now. This is where the science of orbital mechanics gets incredibly messy, and small uncertainties can snowball into massive errors. When astronomers first spot an asteroid, they only have a handful of data points, a few positions in the sky over a short period. From that, they must calculate an entire orbit around the Sun, which is like trying to predict the entire path of a thrown ball after only seeing it for the first fraction of a second. The initial calculations give a rough trajectory, but it is far from precise. This predicted path is usually represented as a cloud of possibilities, a set of potential orbits, rather than a single, certain line. The longer we track an object, the more observations we gather, and the narrower that cloud becomes, refining the prediction. However, for many asteroids, especially newly discovered ones, we simply do not have enough data to be sure. This uncertainty is not due to a mistake or lack of skill. It is a fundamental property of physics and observation. The gravitational pull of every single body in the solar system, from the sun and planets down to large moons, constantly tugs on these asteroids, ever so slightly altering their paths. Jupiter, being the solar system's gravitational heavyweight, is a major player here. Its immense gravity can act like a slingshot, subtly or dramatically changing an asteroid's orbit over time. An object that seems perfectly safe, passing harmlessly by Earth for centuries, could have its orbit perturbed by a close encounter with Jupiter, putting it on a collision course with us many years later. This chaotic interaction is a core reason why a simple initial all clear is never truly final. Another subtle but powerful force is the Yarkovsky effect. This is not gravity. It is a thermal phenomenon. As an asteroid spins, the side facing the Sun heats up. Later, as that heated side rotates away from the Sun, it radiates that thermal energy back into space. This emission of photons acts like a tiny, continuous rocket thruster. The direction and strength of this push depend on the asteroid's rotation rate, its shape, its surface composition, and its orientation. For a large asteroid over many decades, this minuscule push can accumulate enough to change its velocity by thousands of miles, completely altering its future path through the solar system. The problem is that the Yarkovsky effect is incredibly difficult to measure and model accurately. We need to know detailed properties of the asteroid that we often cannot get from simple telescopic observations. We would need to know if it is a fast or slow rotator, whether its surface is rough or smooth, and what it is made of. Is it a pile of rubble or a solid chunk of metal? Without a dedicated spacecraft mission to study a specific asteroid up close, our predictions will always contain this inherent fuzziness. This means that an asteroid predicted to miss Earth by a comfortable margin might, due to the Yarkovsky effect, drift into a keyhole, a precise gravitational corridor that would send it directly into Earth on a future orbit. The responsibility then falls on us to constantly monitor and update the trajectories of known objects. It is not a one-and-done calculation. It is a lifelong vigil for each potentially hazardous asteroid. Our defense strategies must be built around this reality. Any plan to deflect an asteroid has to account for the fact that its trajectory is a moving target. We might launch a spacecraft to nudge an asteroid, but during the years it takes for that spacecraft to reach its target, our understanding of the asteroid's path will have improved. The initial deflection plan, based on old data, might now be slightly off. Therefore, the deflection vehicle itself needs to be smart and adaptable. It must have advanced navigation systems that can autonomously update its course based on real-time observations of the asteroid as it approaches. The mission must be designed with a margin for error, capable of making last-minute corrections. This is part of why the simple Hollywood solution of just blowing up an asteroid is so fraught with danger. If our trajectory knowledge is even slightly imperfect, we might fragment the object, creating a shotgun blast of debris whose paths are even harder to predict and could still cause widespread devastation. The preferred method, a gentle, slow push executed years in advance, is the only way to manage this uncertainty. By applying a small force over a long time, we can gradually shift the asteroid's path, and we can continuously monitor and adjust the effort as our trajectory models improve. This approach requires immense patience and foresight, something that is challenging for political systems often focused on short-term results. The financial and technological investment in such a capability is not just about building one spacecraft. It is about maintaining a permanent readiness to launch, having the rockets and infrastructure on standby, and funding the continuous observational network that feeds it data. Public understanding of this nuanced challenge is crucial. It is easy to think that once we find an asteroid, the problem is solved. But the truth is that the finding is just the beginning of a long, uncertain journey of prediction. Every new observation, from a telescope on a clear night or a space-based observatory, helps shrink that cloud of possible futures, increasing our confidence. International data sharing becomes even more critical here, as observations from different points on the globe and in space help triangulate and refine an object's position with greater accuracy. The Minor Planet Center, which collects and disseminates this data globally, is the unsung hero in this effort, allowing astronomers worldwide to contribute to a collective, ever-improving map of our celestial neighborhood. In a way, defending Earth is less about a single heroic act and more about the persistent, meticulous work of tracking and modelling, of acknowledging that our knowledge is always provisional and must be constantly updated. This acceptance of uncertainty is not a weakness, but a strength, as it drives the need for robust, flexible systems. The development of more powerful computers allows for more complex simulations that can factor in the Yarkovsky effect and gravitational perturbations from dozens of bodies simultaneously. Machine learning algorithms are now being applied to sift through historical data and identify subtle orbital changes that might have been missed. Yet, for all our technology, we are still at the mercy of the fundamental laws of physics, which do not guarantee certainty. This is why the timeline for action is so important. The earlier we identify a threat, the more time we have to watch it, to understand its drift, and to plan a measured response. A last-minute discovery leaves no room for error and forces us into drastic, high-risk options. The challenge of trajectory prediction, therefore, is inextricably linked to the challenge of detection. One cannot work without the other. A perfect detection system is useless if we cannot accurately forecast paths. And sophisticated prediction models are meaningless if we do not have the objects in our catalogue to begin with. It is a symbiotic relationship that forms the bedrock of any credible planetary defense strategy. As we look to the future, improving our predictive capabilities means investing not only in bigger telescopes, but also in specialized missions to characterize asteroids, to measure their rotation, their composition, and their thermal properties firsthand. Each such mission provides a template, a data point that helps us better understand and model the entire population. The ongoing effort to track, predict, and understand is a testament to human curiosity and our desire to protect our home. It is a complex, never-ending puzzle, but with each passing year and each new discovery, we get a little better at reading the celestial map and navigating the potential hazards it contains. The uncertainty will always be there, but through diligent work and global cooperation, we can learn to manage it, ensuring that we are never caught off guard by a threat we saw coming but failed to understand fully. The journey from a blurry initial detection to a confident, precise trajectory is a long one, but it is a journey we must commit to for the long haul, for the safety of generations to come. This continuous refinement process is what turns a statistical probability into an actionable certainty or a reassuring all clear. It is the quiet, behind-the-scenes work that makes the dramatic, movie-style saves possible, and it deserves every bit as much attention and support as the more visible aspects of space defense. So the next time you hear about a new asteroid discovery, remember that the story does not end there. It is just the first chapter in a long and intricate tale of prediction and precision. But even after we've painstakingly tracked an asteroid and refined its trajectory, we face a fundamental problem that makes any defensive action incredibly risky. Not all asteroids are created equal. Imagine finally spotting that storm on the horizon, only to realize you have no idea if it's a simple thunderhead or a supercell tornado. Your preparation would be entirely different. In the same way, asteroids come in a stunning variety of compositions, structures, and internal strengths, and this diversity dictates every single choice we would have to make in a planetary defense scenario. The popular image of an asteroid is a solid, monolithic rock floating through space, but that is rarely the case. Many, perhaps even most, are what scientists call rubble piles. These are not solid objects at all, but rather loose collections of boulders, gravel, dust, and ice, all held together by the most minuscule gravitational attraction. They have very little internal strength. Think of them as giant, cosmic sandcastles. The asteroid Itokawa, visited by the Japanese Hayabusa probe, is a perfect example, a porous, gravelly assemblage that looks like it could fall apart at any moment. Then, on the complete other end of the spectrum, you have metallic asteroids. These are the remnants of ancient proto-planet cores, incredibly dense and solid chunks of iron and nickel. They are the tanks of the solar system, massively heavy and incredibly tough. And there are everything in between. Stony asteroids, carbonaceous chondrites full of clay and organic compounds, and mixtures of all of the above. This variety is not just a scientific curiosity, it is the central dilemma of planetary defense. A deflection technique that works beautifully on one type could be a catastrophic failure on another. Consider the kinetic impactor method, like the DART mission, which involves slamming a spacecraft into an asteroid to change its speed. If you fire a kinetic impactor at a rubble pile, you might not nudge it. Instead, you might just blow a hole in it, scattering the debris. The asteroid could disassemble into a cloud of smaller, but still very dangerous, rocks. Now, instead of dealing with one predictable impactor, you would be facing a shotgun blast of fragments, each on its own unpredictable path toward Earth. Some might burn up in the atmosphere, but many could get through, causing multiple impacts over a vast area. You would have turned a single problem into a global catastrophe. Conversely, if you try that same kinetic impactor on a solid metallic asteroid, it might be completely ineffective. The impact could be like throwing a pebble at a battleship. The spacecraft would just vaporize on impact, transferring a negligible amount of momentum and barely altering the asteroid's course. The sheer density and mass of a metallic object would require a much more powerful impact, or perhaps multiple impacts, to achieve the same velocity change you could get on a lighter, rubble pile asteroid. This is why the simple, Hollywood-style solution of just blowing up an asteroid with a nuclear weapon is so terrifyingly simplistic. The outcome is entirely dependent on what you are blowing up. For a loosely bound rubble pile, a nuclear detonation, even at a standoff distance, might not push it coherently. It might simply shatter it, creating that same deadly cloud of fragments. For a solid metallic asteroid, the explosion might only gouge out a crater, doing little to change its overall trajectory. The energy required to effectively move or disrupt these different types varies astronomically. This means that before we can even think about launching a deflection mission, we absolutely must know exactly what we are dealing with. We need to characterize the target asteroid in immense detail. This is a mission in and of itself, a complex and time-consuming endeavor that requires sending a dedicated spacecraft to rendezvous with the asteroid, orbit it, map it, and study its properties. We would need to determine its mass, its density, dot, its internal structure, its rotation rate, its surface composition, and its overall cohesion. Is it a single solid body? Is it a rubble pile? Is it a binary system with a moonlet? Techniques like radar imaging from Earth can give us some clues about shape and rotation, but they cannot tell us about internal structure. For that, you need to get up close. A characterization mission might use radar to probe the interior, take high-resolution images to map the surface features and boulder distribution, and even use a gravimeter to measure the gravitational field, which reveals how the mass is distributed inside. All of this data is crucial for choosing the right deflection strategy and for modelling exactly how the asteroid will respond to our intervention. For a rubble pile, a gentle, sustained push might be the only safe option. One proposed method is the gravity tractor, where a spacecraft simply hovers near the asteroid for months or years, using its own tiny gravitational pull to slowly tug the asteroid onto a new path. This method is safe because it never physically touches the asteroid, so there is no risk of fragmentation. However, it requires a very long lead time and a powerful, efficient propulsion system for the spacecraft. Another idea for a rubble pile is to use a focused laser or a swarm of smaller spacecraft to ablate material from the surface. The ejected material acts like rocket exhaust, pushing the asteroid in the opposite direction. But again, this requires a deep understanding of the surface composition to be effective. For a solid metallic asteroid, a more aggressive approach might be necessary, such as a much larger kinetic impactor or even the controversial use of a nuclear device for a standoff burst that vaporizes surface material to create a thrust. The time factor becomes critical here. A characterization mission can take years to plan, launch, and execute. If we discover a threatening asteroid with only a short warning time, we may not have the luxury of sending a scout mission first. We might be forced to act with incomplete information. gambling on a deflection method based on best guesses from remote observations. This is a terrifying prospect. The wrong guess could doom us. This diversity also extends to their orbits and how they behave. A fast-spinning rubble pile might be actively flinging material off its surface, which could pose a hazard to any approaching spacecraft. A carbonaceous asteroid, rich in water and volatiles, might outgas when heated by the sun, adding another unpredictable force. Similar to the Yarkovsky effect, that changes its trajectory. Every new layer of complexity makes the defense problem harder. Furthermore, the physical nature of the asteroid affects how we observe it from Earth. Dark, carbonaceous asteroids are harder to track than bright, stony ones. A rubble pile might have a very irregular shape, which causes its brightness to vary dramatically as it rotates, making precise trajectory measurements more difficult. This ties back directly to the prediction challenges we discussed. An asteroid we cannot characterize well is an asteroid whose path we cannot predict with ultimate confidence. The need for robust characterization drives the need for a ready fleet of spacecraft, or at least versatile spacecraft platforms that can be adapted to different missions on short notice. It also underscores the importance of studying asteroids that are not currently threats. Every mission to a near-Earth asteroid, whether it's OSIR-ISR-EX or Hayabusa 2, provides invaluable data that helps us build models for the entire population. We learn about the range of densities, the commonality of rubble piles, and the mechanical properties of different materials in microgravity. This knowledge bank is our first line of defense. It allows us to make better inferences from remote observations when time is short. So, when we talk about building a planetary shield, we are not talking about a single weapon. We are talking about a sophisticated toolkit. And the most important tool in that kit is knowledge. The ability to quickly and accurately diagnose the nature of the threat is what separates a successful deflection from a disastrous miscalculation. It means that our planetary defense strategy must be deeply integrated, with detection telescopes feeding data to trajectory modelers, who then inform the engineers designing the characterization and deflection missions. It is a chain of knowledge, and any weak link can break the entire effort. The diversity of asteroids is therefore not just a scientific challenge, it is the core operational challenge. It means that there is no silver bullet, no one-size-fits-all solution. Our approach must be as nuanced and varied as the enemies we face. It demands humility, because we are dealing with objects that have been shaped by billions of years of solar system history, each with its own unique story and structure. Overcoming this challenge requires a sustained commitment to exploration and science, for it is only by understanding these celestial objects intimately that we can hope to safely steer them away from our home. The task is monumental, but it begins with acknowledging a simple, crucial truth. In space, every rock tells a different story, and we must learn to read each one before we can write its final chapter. This process of learning is continuous, and every new asteroid we visit adds a piece to the puzzle, making our planetary defense capabilities more robust and reliable for the future. The journey is long, but with each step, we become better guardians of our planet. So, now that we understand how crucial it is to know exactly what kind of asteroid we're facing, the next logical question is, what do we actually do about it? This is where we move from diagnosis to treatment, and it forces us to confront a classic sci-fi trope head-on, the idea of simply blowing the threat to smithereens. It sounds satisfying and decisive, like something out of an action movie, but in reality, it's probably the worst thing we could do. The fundamental problem with destruction is the lesson of the fragments. You might successfully shatter a large asteroid, But you haven't made the threat disappear. You've just transformed a single, predictable bullet into an unpredictable shotgun blast of debris. Each one of those fragments, depending on its size, could still retain enough energy to cause catastrophic damage if it reaches Earth's atmosphere. Instead of one impact point, you could now have multiple impacts scattered across a vast area, or even a rain of debris that heats up the upper atmosphere and causes widespread firestorms. The situation goes from bad to exponentially worse because tracking all those new, smaller pieces becomes nearly impossible, and predicting where they will land is a nightmare. This is why the scientific community overwhelmingly favours a different approach: deflection. The goal of deflection isn't to destroy the asteroid, but to gently nudge it, to change its velocity just enough over a long period so that it misses Earth entirely. It's a far more subtle and patient strategy, but it's also far safer. Think of it like this. If a car is heading for a crowd, you don't try to vaporize the car with a rocket, because the shrapnel would still hurt people. Instead, you want to slowly push the steering wheel from a distance, guiding the car safely away from the crowd. That's the core idea behind deflection. It requires a deep understanding of orbital mechanics and a lot of advanced warning, but it avoids the uncontrollable chaos of fragmentation. The key to making deflection work is time. The earlier we can act, the smaller the nudge needs to be. A tiny change in velocity, just a few centimeters per second, applied years or even decades before a predicted impact, can translate into a miss of thousands or millions of miles by the time the asteroid crosses Earth's orbit. This is because the small velocity change accumulates over the vast distance the asteroid travels. The further out we can make this adjustment, the less energy is required, and the more control we have over the outcome. So, how do we actually deliver this nudge? There are several proposed methods, each with its own advantages and challenges. The one we've already tested to some degree is the kinetic impactor. This is essentially what the DART mission was all about. You launch a spacecraft and have it crash into the asteroid at high speed. The transfer of momentum from the spacecraft to the asteroid, like a cosmic pool shot, imparts a slight change in the asteroid's velocity. DART proved this can work, but it was a test on a small, non-threatening moonlet. Scaling this up to a large dot, potentially hazardous asteroid is a different matter. The effectiveness depends heavily on the asteroid's mass and composition, which is why that prior characterization mission is so vital. For a solid asteroid, it might work well, but for a rubble pile, it might just create a crater and scatter material, reducing the momentum transfer or making things worse. Another elegant idea is the gravity tractor. This doesn't involve any physical contact at all. A spacecraft would fly alongside the asteroid for a long period, perhaps years, and use its own gravitational pull to gently tug the asteroid off course. It's an incredibly slow process, but it's also very safe and controlled. The spacecraft would need to have a substantial mass and a highly efficient propulsion system to maintain its position relative to the asteroid for such a long time. There's no risk of breaking the asteroid apart, and the effect, while small, is continuous and predictable. This method would be ideal for a rubble pile where any physical impact is too risky. Other concepts involve using focused energy. One idea is to use a powerful laser, or an array of mirrors to concentrate sunlight, to ablate the surface of the asteroid. This means heating up a spot on the surface until material vaporizes and jets away. The reaction force from this jet of gas acts like a tiny rocket engine, slowly pushing the asteroid in the opposite direction. Again, this is a slow and steady method that requires a long duration to be effective. Another more futuristic concept involves painting part of the asteroid to alter its albedo, or how reflective it is. by changing the amount of sunlight it absorbs. You could theoretically influence the Yarkovsky effect, using the asteroid's own heat radiation to gradually change its path over many years. The common thread with all these deflection methods is that they are gradual. They are about management and precision, not about brute force. This is a complete paradigm shift from how we often think about solving problems. Our instinct is to hit something hard to stop it, but in space, that instinct can lead to disaster. The destruction approach, typically involving nuclear explosives, is now generally considered a last resort option, only for scenarios where we have very little warning time and the asteroid is too large for deflection to work in the available time. Even then, the goal wouldn't be to shatter the asteroid, but to use the explosion as a standoff push. The idea is to detonate a device at a certain distance from the surface, so that the X-rays and heat vaporize a layer of the asteroid, creating a jet of material that thrusts the main body away. This is still a form of deflection, albeit a much more violent and risky one. The problem is that it's incredibly difficult to model how an asteroid would respond to such a blast. Would it push it coherently, or would it fracture it? The outcome is highly uncertain, which is why it's an option of desperation. This highlights the critical link between detection, characterization, and deflection. A robust planetary defense system isn't just about having a weapon. It's about having the entire chain of intelligence and response. We need the telescopes to find the threat early, the missions to study it and understand its nature, and then the appropriate technology ready to launch and execute the chosen deflection strategy. The deflection method we choose must be tailored to the asteroid. A gravity tractor might be perfect for a small, rubble pile asteroid discovered decades in advance. A kinetic impactor might be suitable for a larger, solid asteroid if we have enough lead time. And in a worst-case scenario, a nuclear standoff burst might be the only card left to play, despite its enormous risks and political complications. The decision-making process itself is another layer of complexity. Who gets to decide which method to use? It would require a global consensus. Based on the best available scientific data, there's no room for error or hesitation. This is why ongoing research and development in all these areas is so important. We need to advance each of these technologies so that when the time comes, we have a full toolkit to choose from, not just one untested idea. Public education is also key here. The movie image of heroes blowing up an asteroid is deeply ingrained, so it's important to explain why the quieter, more patient approach of deflection is actually the smarter and safer path. It's about playing the long game with the solar system. It requires foresight, international cooperation, and a commitment to funding the science and engineering behind these methods. The success of DART was a huge step forward, but it was just one test of one method under ideal conditions. We need more tests, more demonstrations, and more missions to build our confidence. We need to practice on other harmless asteroids to refine the techniques for gravity tractors or laser ablation. Every bit of knowledge we gain makes our planetary defense more robust. So, while the idea of destruction might be more dramatic, the reality is that deflection is the careful, calculated strategy that truly offers a way to protect our planet without unleashing a new set of dangers. It acknowledges that, in space, finesse often triumphs over force, and that the safest way to avoid a collision is to never let it happen in the first place by gently guiding the threat away on a new path. This philosophy extends to how we think about the entire endeavour. Building a planetary defence isn't about creating a war machine against asteroids. It's about becoming skilled navigators of our cosmic neighbourhood, learning to work with the physics of the solar system to ensure a safe passage for Earth. It's a testament to human ingenuity that we can even contemplate such a thing, but it also demands humility. because we are dealing with forces and objects on a scale that can humble any civilization. The choice between deflection and destruction is therefore more than a technical decision. It's a statement about how we choose to confront existential threats. Do we react with chaotic, potentially self-destructive violence, or do we respond with measured, intelligent, and persistent action for the future of our world? The answer must be the latter. The lesson of the fragments is clear. Breaking something apart rarely solves the problem, but understanding it and guiding it wisely often does. This principle will guide us as we continue to explore the challenges and solutions in safeguarding our planet from celestial impacts. The journey is complex, but with each step, we become more capable stewards of our shared home in the cosmos. The patience required for deflection mirrors the patience needed for the entire planetary defense effort. It's a long-term commitment to vigilance, science, and international collaboration. And in that commitment lies our best hope for a secure future. The conversation about deflection naturally leads us to one of the most tangible methods we have actually tested, the kinetic impactor. This is the concept of literally hitting an asteroid with a spacecraft to change its speed. And while it sounds straightforward, the execution is one of the most difficult engineering challenges humanity has ever faced. The successful DART mission proved the principle, but that was a carefully orchestrated test on a small, non-threatening moonlet with a known orbit. Applying this to a real, potentially civilization-ending asteroid is a completely different ballgame. The core challenge is hitting a target that is essentially a mountain-sized object moving at tens of thousands of miles per hour, millions of miles away from Earth. The precision required is almost unimaginable. At those distances and speeds, you cannot joystick the spacecraft from the ground. The time delay for radio signals can be many minutes, meaning by the time we see a problem from Earth, it is far too late to send a correction. Therefore, the spacecraft must be completely autonomous during its final approach. It has to see the asteroid, distinguish it from the background stars, and guide itself to a precise impact point, all while both objects are moving at hypersonic velocities. This requires incredibly sophisticated onboard computing and navigation software. The spacecraft uses a system called optical navigation, where its camera takes images of the target asteroid and a nearby star field. By comparing the asteroid's position relative to the stars, the onboard computer can calculate its own trajectory and make tiny course corrections using its thrusters. In the final hours and minutes, this system has to work flawlessly. For DART, the algorithm had to identify the small moonlet, Dimorphos, and then specifically target it, ignoring the larger asteroid it was orbiting. This is like trying to hit a specific pebble orbiting a larger rock, while both are hurtling through space. The margin for error is tiny. A miss by even a small distance could mean the difference between a successful deflection and a complete waste of effort. The impact itself is not a gentle tap. The spacecraft is travelling so fast that upon collision, it is completely vaporized in a flash of plasma and energy. The goal is to transfer as much of its momentum as possible to the asteroid. This momentum transfer is what provides the nudge, changing the asteroid's velocity by a small but critical amount. The effectiveness of this momentum transfer depends heavily on the asteroid's composition, which we discussed earlier. A rubble pile might absorb the impact poorly, ejecting a lot of material and reducing the push, while a solid metallic body might be too massive to budge significantly. This is why a reconnaissance mission is so often a prerequisite. We need to know what we are hitting to calculate the required size and speed of the impactor. The spacecraft itself must be a rugged, purpose-built machine. It is not a delicate science probe. It is a bullet. It needs to be sturdy enough to survive the journey and the intense radiation environment of space. And its structure must be designed to withstand the final moments of approach without breaking apart prematurely. The guidance system must be hardened against faults and capable of dealing with unexpected surprises, like the asteroid having an irregular shape or a very dark, difficult to image surface. The mission planners also have to choose the exact point of impact carefully. Hitting the center of mass might be the most efficient for a pure push, but sometimes an off-center impact might be preferable to induce a spin, which can also help alter the trajectory over time through the Yarkovsky effect. The amount of energy involved is staggering. A kinetic impactor for a large asteroid would need to carry a significant mass, requiring a powerful rocket to launch it on its way. This brings up the issue of launch windows and timing. We need to launch years in advance to ensure the spacecraft can intercept the asteroid at the correct point in its orbit. Any delay in launch or a problem during the cruise phase could mean missing the interception window entirely. Furthermore, we likely would not rely on a single impactor for a truly large threat. A coordinated swarm of impactors might be necessary, each one hitting in sequence to build up the velocity change. Coordinating such a swarm adds another layer of complexity, with multiple spacecraft needing to navigate autonomously and impact at precisely calculated times and locations. The development and testing of this autonomous navigation technology are ongoing. Missions like DART provide invaluable data. But we need more tests on different types of asteroids to refine our models and improve the software. We are essentially teaching machines how to be cosmic sharpshooters. The software algorithms use feature tracking and pattern recognition to lock onto the target. As the spacecraft gets closer, the asteroid grows from a single pixel into a detailed world, and the navigation system must continuously update its aim based on the actual shape and rotation it observes. This is not a pre-programmed path. It is a real-time, dynamic process. The consequences of failure are absolute. If the navigation system fails and the spacecraft misses, we have wasted precious years and resources, and the asteroid continues on its path unabated. Even a partial success, where the impact happens but does not transfer enough momentum, could be disastrous if it only slightly alters the impact point without actually preventing the collision. This technology also has limitations based on the size of the asteroid. For a truly massive object, like the one that wiped out the dinosaurs, a kinetic impactor might be like a mosquito hitting a car. The effect would be negligible. For those kinds of existential threats, other methods, like nuclear deflection, might be the only viable option, despite their own set of risks and political challenges. Therefore, kinetic impact is not a silver bullet. It is a tool in the toolbox, best suited for asteroids of a certain size and with sufficient warning time. Its beauty lies in its simplicity. It uses pure physics without exotic technology, but its implementation is brutally complex. The future of this technology involves building larger impactors, improving the autonomy and intelligence of the navigation systems, and integrating it with other methods. For instance, a kinetic impact could be followed by a gravity tractor to fine-tune the deflection, or used to create a crater for a more effective standoff nuclear burst if absolutely necessary. The international collaboration required is also significant. The technology and expertise for such missions are not held by one country. Sharing data, resources, and launch capabilities will be essential for mounting a credible planetary defense. Public support and funding are equally crucial. While the DART mission was a brilliant success, it was a single demonstration. We need a sustained program of development and testing to be truly prepared. This means investing in new spacecraft designs, more powerful rockets, and advanced simulation software that can model millions of different impact scenarios. In conclusion, The technology of kinetic impact is a proven concept, but its application in a real crisis is a high-stakes gamble that depends on perfect execution, deep knowledge of the enemy, and an unwavering commitment to getting the details right. It represents a remarkable fusion of celestial mechanics, software engineering, and sheer courage, aiming to protect our planet by playing a cosmic game of billiards with the very building blocks of our solar system. The journey to perfect this technology is ongoing, and every test, every simulation, and every new discovery brings us one step closer to being able to confidently deflect a threat and secure our future. The challenge is immense, but the alternative is unthinkable, driving us to push the boundaries of what is possible in our quest to safeguard humanity. The precision required is a testament to human ingenuity, and the success of such a mission would stand as one of our greatest achievements as we continue to explore the cosmos. Developing and refining these defensive capabilities is not just a scientific endeavor, it is a moral imperative for the long-term survival of our civilization. The knowledge that we are developing the means to prevent a catastrophe is a powerful motivator, and the technology of kinetic impact is a key part of that global defense strategy. It is a practical, tested method that turns a theoretical concept into an actionable plan, giving us a fighting chance against the random hazards of space. The work is hard, the margins are slim, but the payoff is the continued existence of our world and everything on it. This makes the pursuit of this technology one of the most important and inspiring missions we can undertake as a species. But when kinetic impactors just won't cut it, because the asteroid is too massive or the warning time is too short, the conversation inevitably turns to the most powerful tool in our theoretical toolbox: nuclear explosives. This is the option that sounds like it's straight out of a blockbuster movie, but in reality, it's a deeply complex and controversial last resort, fraught with both technical and political dangers. On the surface, the idea seems straightforward. A nuclear device possesses an immense amount of energy, and that energy could, in theory, be used to push an asteroid off course. The concept isn't to blow it up like in the films. The preferred method is a standoff burst. You detonate the device at a calculated distance from the asteroid's surface. The intense X-rays and heat from the explosion would vaporize a layer of the surface material, and the rapid expansion of that vaporized rock would act like a jet, thrusting the main body of the asteroid in the opposite direction. It's a way of using the bomb not as a weapon of destruction, but as a supremely powerful, one-time use rocket engine. The appeal is obvious. For a very large asteroid, or one we discover with only a few years or months of warning, a nuclear device might be the only thing with enough energy to make a difference where a kinetic impactor would be futile. However, the technical execution is a minefield of uncertainties. Predicting exactly how an asteroid would respond to a nuclear blast is incredibly difficult. The outcome depends entirely on the asteroid's composition and structure, which we might not have time to fully characterize. If it's a solid, monolithic rock, the standoff burst might work as intended, creating a strong, coherent push. But if it's a rubble pile, a loose collection of rocks held together by gravity, the explosion might not push it evenly. It could instead shatter it, breaking the asteroid into a swarm of smaller but still deadly fragments. Now, instead of one impactor, you have dozens or hundreds, each on an unpredictable path, potentially turning a single catastrophic event into a global bombardment. The resulting fragments could range in size from dust to city killers, and tracking all of them would be impossible. This fragmentation risk is the primary technical reason scientists are so wary. Furthermore, there's the issue of radioactivity. If the device detonates close enough to vaporize surface material, some of that material could become irradiated. while most of the radioactive fallout would be dispersed into space. Any fragments that do eventually reach Earth could carry trace amounts of radioactivity, posing a secondary environmental and health hazard. The blast itself also has to be perfectly calibrated. The standoff distance is critical. Too close and you risk fragmentation. Too far and the energy dissipates without providing a sufficient push. We have limited data on how materials behave under such extreme conditions in the vacuum of space, making reliable simulation a challenge. This leads us to the other, even more formidable obstacle: the political and legal quagmire. The use of nuclear weapons in space is explicitly prohibited by the 1967 Outer Space Treaty. This treaty, signed by most spacefaring nations, bans the placement of nuclear weapons or any other weapons of mass destruction in orbit, on the Moon, or on any other celestial body. Deploying a nuclear device for asteroid deflection, even with peaceful intentions, would likely be interpreted as a violation of this treaty. It would require a renegotiation or a special exemption, which would involve a diplomatic nightmare, getting the entire international community, including rivals and adversaries, to agree to launch a nuclear device into space is a tall order. The mere proposal would trigger a global geopolitical crisis. Many countries would view it with extreme suspicion, questioning the true intentions behind the mission. Is it really for planetary defense, or is it a pretext for testing or deploying nuclear weapons in space? This could lead to a new arms race, with nations feeling compelled to develop their own space-based nuclear capabilities under the guise of planetary defense. Trust is a fragile commodity in international relations, and a nuclear deflection mission would strain it to the breaking point. The decision-making process itself would be paralyzed by politics. Who gets to authorize the use of a nuclear device? Which nation or international body holds the button? The United Nations Security Council, a newly formed scientific committee. Achieving consensus would be slow and difficult, and in a scenario where time is of the essence, such delays could be fatal. There's also the terrifying precedent it would set. Once we cross the line and use a nuclear weapon in space, even for a benevolent purpose, it normalizes the idea. It makes it easier for another nation to justify its own nuclear tests or deployments in the future, potentially for less peaceful reasons. The weaponization of space is a line many have worked hard to avoid crossing, and a nuclear deflection mission could irrevocably erase that boundary. Beyond politics, there are immense practical hurdles. Developing and building a nuclear device specifically for space use would be a massive undertaking. It would need to be rugged enough to survive a rocket launch and a long journey through space. And its detonation mechanism would have to be incredibly reliable. We would also need a delivery system, a spacecraft capable of carrying the device and placing it at the precise standoff distance with the same level of autonomous navigation required for a kinetic impactor. This is not a technology we have readily available. It would require a significant research and development program, which itself would be controversial and expensive. Public perception is another huge factor. The idea of launching a nuclear bomb into space would understandably cause widespread fear and opposition. People would worry about launch failures, accidental detonations, or the device falling into the wrong hands. Convincing the global population that this is a necessary risk would be a monumental communications challenge. So, where does this leave us? The nuclear option remains on the table, but only as a last-ditch effort for a specific set of circumstances. A large, extinction-level asteroid discovered with too little time for any other method to work. In such a dire scenario, the calculated risk of using a nuclear device might be deemed preferable to the certainty of global annihilation, but for anything less than that, the political, legal, and technical risks are so profound that the international community would likely exhaust every other possibility first. This highlights the critical importance of early detection and investment in non-nuclear deflection technologies. The best way to avoid the nuclear dilemma is to never be in a situation where it's our only option. We need to strengthen our detection networks to give us the decades of warning that make gentle deflection methods like gravity tractors feasible. The nuclear question is ultimately a reflection of a deeper issue. Planetary defense cannot be separated from global politics. It forces us to confront our own divisions and ask whether humanity can unite to face a common threat. Even when the tool required is shrouded in fear and historical baggage, it's a dangerous game, one where the stakes are the highest imaginable, and every move must be considered with the utmost caution. The technical challenges are daunting, but the political ones may be even greater. Overcoming them would require a level of transparency, trust, and cooperation that we have rarely achieved as a species. Until then, the nuclear option remains a spectre in the background, a powerful but perilous solution we hope we never have to use. The very fact that we are discussing it seriously shows how high the stakes are in protecting our planet. And it should motivate us to pursue all other avenues with even greater urgency. The development of any planetary defense system must include frank and open international discussions about the rules of engagement for such extreme measures, establishing clear protocols long before a crisis emerges. This proactive diplomacy is just as important as the engineering breakthroughs. Without it, we risk being paralyzed by indecision when every second counts. The nuclear option is a reminder that our greatest challenges in defending Earth may not be out in the cosmos, but right here at home, in our ability to work together for the common good. It underscores that saving the world requires more than just advanced technology. It demands wisdom, foresight, and a shared commitment to peace. So, while we continue to research and develop all possible deflection methods, we must also build the global frameworks that would allow us to use them responsibly, ensuring that our solution to one threat does not create another, even more dangerous one. The path forward is narrow and fraught with peril, but it is a path we must navigate with care, for the sake of every future generation. But even if we could somehow navigate the political minefield of the nuclear option, we would immediately slam into the next, perhaps even more fundamental wall: the sheer, mind-boggling cost of building and maintaining any kind of planetary defense system. Let's be brutally honest here. Creating a global shield against asteroids would be the single most expensive project in human history, dwarfing the Apollo program, the International Space Station, and every other mega project combined. We are talking about costs that could easily run into the hundreds of billions, even trillions of dollars. This isn't just about building one or two spacecraft. It's about funding a permanent, multi-generational enterprise. The financial burden raises an immediate and difficult question: who pays for the salvation of the planet? Is this a global effort, where every nation contributes according to its means, or would it be led by a handful of wealthy, spacefaring nations? The history of international projects is a mixed bag. The International Space Station shows that cooperation is possible, but it also involved complex negotiations, political horse trading, and constant budgetary scrutiny. For an asteroid defense system, the stakes are infinitely higher, and so is the potential for disagreement. Imagine trying to get every country on Earth to agree on a funding formula. Would it be based on GDP, population, historical carbon emissions? The debates would be endless and incredibly divisive. Some nations might argue that the countries with the most advanced space capabilities should bear the brunt of the cost, while others might insist on a more equitable distribution of both financial burden and decision-making power. Then there's the even tougher challenge of convincing governments and their citizens to spend such a colossal amount of money on a threat that, while catastrophic, has a very low probability of happening in our lifetimes. This is the classic problem of a high consequence, low probability event. For a politician facing re-election every few years, it's incredibly difficult to justify allocating tens of billions of dollars to a problem that might not materialize for centuries when there are immediate, visible crises demanding attention and resources. Think about the pressing issues we face today: climate change, poverty, disease, hunger, crumbling infrastructure. These are real, tangible problems affecting millions of people right now. How do you tell a community that needs a new hospital or a school that their tax money is instead going to a space-based telescope to look for rocks that will probably never hit us? The political will for such a long-term investment is fragile and easily broken. This is where the psychology of risk works against us. Our brains are wired to respond to immediate, visible threats, not abstract, far-off possibilities. An asteroid impact is a statistical concept, not something we can see or feel until it's too late. This complacency is perhaps the greatest enemy of planetary defense funding, without a recent, vivid reminder of the danger, like a significant near miss or a smaller impact causing damage. It's an uphill battle to maintain funding and focus. The cost isn't a one-time thing, either. It's a continuous drain on resources. You have to pay for the initial research and development, which is enormous. We would need to design and build new classes of spacecraft: kinetic impactors, gravity tractors, characterization probes, and possibly even nuclear delivery vehicles. This requires cutting-edge technology and propulsion, navigation, materials, science, and autonomous systems. Then there's the launch infrastructure. We would need a fleet of heavy-lift rockets, like the SpaceX Starship or its successors, capable of launching these massive payloads into space reliably and frequently. Building and maintaining that launch capacity is astronomically expensive. Furthermore, you need the global network of telescopes and sensors, both on Earth and in space, to constantly monitor the skies. Projects like the Vera-C, Rubin Observatory, and NASA's NEO Surveyor are crucial steps, but they are just the beginning. A comprehensive survey requires multiple telescopes in different orbits to eliminate blind spots, especially the one caused by the Sun. This network needs to be operated, maintained, and upgraded over decades and centuries. The data from these telescopes must be processed by powerful supercomputers running complex orbital simulation software, all of which requires a dedicated team of scientists, engineers, and technicians. This is a permanent workforce that needs salaries, benefits, and facilities. The logistics of coordinating all this are a nightmare. It's a system of systems that must work in perfect harmony. A failure in any part, a telescope going offline, a software bug, a rocket explosion, a funding cut in one country could create a gap in our defences at the worst possible moment. This interconnectedness means that the system is only as strong as its weakest link, and ensuring global reliability adds another layer of cost and complexity. Another major hurdle is the economic disparity between nations. How do you ask a developing nation struggling with basic needs to contribute millions to a space defense program? It's a hard sell. This could lead to a situation where only a few wealthy nations build the system, which then raises the question of control. If one country or a small group of countries owns and operates the planetary defense system, do they get to make all the decisions? What if a decision to deflect an asteroid inadvertently shifts the risk to another part of the world? The nation controlling the system might be accused of prioritizing its own safety over others. This could create geopolitical tensions and undermine the very cooperation needed for the system to be legitimate and trusted. The funding model itself is unclear. Would it be managed by the United Nations, a new, independent international agency? Would it be funded through voluntary contributions, which are often unreliable, or through a mandatory tax on member states? There is no precedent for a global project of this scale and purpose. Even if the initial funding is secured, maintaining it over the long term is another challenge. Political landscapes change, economies rise and fall, and priorities shift. A system that is funded today could be defunded tomorrow by a new administration that doesn't see the value. This lack of long-term commitment is a critical vulnerability. The project requires a century-scale perspective, but our political and economic systems are inherently short-term. So, how do we overcome this? It requires a fundamental shift in how we view ourselves as a species. We need to start thinking as a planetary civilization, recognizing that some threats transcend national borders and require a unified response. Education is key. Making the public and policymakers aware of the real, albeit statistical, risk is the first step. We can frame it as a global insurance policy. The cost, while immense, is trivial compared to the economic devastation of even a small impact. The Chelyabinsk event in 2013 caused tens of millions of dollars in damage and injured over 1,000 people. And that was from a relatively small object. A larger impact could cause trillions in damage and global economic collapse. Investing in prevention is far cheaper than dealing with the aftermath. We can also leverage technological spin-offs. The research and development for planetary defense will inevitably lead to advancements in other fields, like space propulsion, robotics, and materials science, which can benefit the economy and create new industries. International collaboration can build trust and shared purpose, turning a defensive project into a unifying human endeavour. Ultimately, the question of who pays for planetary defense is a test of our maturity as a civilization. It forces us to decide if we are willing to invest in our collective future, to look beyond immediate crises and secure our place in the cosmos. The logistics are daunting. The cost is prohibitive. But the alternative, doing nothing and hoping we get lucky, is a gamble with the entire planet at stake. Finding a way to fund and build this system is not just a technical or economic challenge. It is the ultimate test of our ability to cooperate on a global scale for the benefit of all humanity. The journey is long, and the price tag is high. But the value of what we are protecting, our only home, is literally beyond measure. We must find a way, because the cost of failure is one we simply cannot afford. This financial and logistical hurdle is perhaps the most human of all the challenges we face, rooted in our politics, our economics, and our psychology. But it is one we must overcome if we are to be the guardians of our own future. The conversation about cost is therefore not a sidebar. It is central to the entire enterprise. Without solving the funding puzzle, all the brilliant engineering and scientific breakthroughs will remain on the drawing board, useless when a real threat emerges. We need to start the difficult, messy, but essential work of building the financial and political frameworks now, before we are forced to by an incoming asteroid. The time to figure out how to pay for our survival is when the sky is still clear, not when we can see the object heading our way. Even if we miraculously solve the funding puzzle and secure the trillions of dollars needed for a planetary defense system, all that money and effort would be completely worthless without one irreplaceable resource: time. The single most critical factor in successfully defending Earth is not the technology or the funding, but the amount of warning time we have. This is the race against the cosmic clock, and it is a race we can only win if we start decades in advance. The fundamental principle of asteroid deflection is that a very small change in velocity, applied early enough, results in a very large missed distance by the time the asteroid reaches Earth's orbit. It is a game of celestial leverage. The further away the asteroid is when we nudge it, the less we have to push it. A velocity change of just 1 centimetre per second, if applied 20 years before impact, can be enough to make an asteroid miss Earth by thousands of miles. However, if we only have 1 year of warning, that same 1 centimetre per second change might only shift the impact point by a few hundred miles, which is utterly useless if the asteroid is still heading for a populated area. This is why early detection is not just important, it is everything. The relationship between time and required energy is not linear. It is exponentially in our favour the earlier we act. For a large asteroid, say 1 kilometre in diameter, the amount of energy needed to change its course significantly is colossal. If we have decades, we can use a gentle, sustained method like a gravity tractor, where a spacecraft hovers near the asteroid for years, using its tiny gravitational pull to slowly tug it off course. This method is safe, predictable, and low risk, but it is also slow. It requires a patient, long-term investment of time. If we have only a few years, our options become dramatically more limited and dangerous. A kinetic impactor might still work, but it would need to be much larger and hit with far greater force to achieve the same velocity change in a shorter period. The window for multiple attempts closes, and the margin for error vanishes. If the first impactor misses or is only partially effective, there may not be time to launch a second one. And if we discover a truly massive, extinction-level asteroid with only a few months or years of warning, our options shrink to a terrifying shortlist. In such a dire scenario, the only tool with enough energy to make a difference in a short time is a nuclear device. We are forced into the very high risk, politically volatile option we desperately want to avoid. The calculation becomes a grim gamble. Is it better to risk fragmenting the asteroid with a nuclear blast, potentially creating multiple impacts, or to accept a single, certain global catastrophe? At that point, evacuation of predicted impact regions might be the only defense left. But for a large impact, evacuation is largely a futile gesture. The societal collapse from the panic alone would be unimaginable, and there is no place on Earth that would be safe from the global climatic effects of a major impact. The ash and dust thrown into the atmosphere would trigger an impact winter, destroying agriculture worldwide and leading to mass starvation. This underscores why a planetary defense system is only effective if it is coupled with a detection network that provides this crucial reaction time. Our current detection capabilities are improving, but are still full of gaps. We have found the vast majority of the very large, civilization-ending asteroids, but we are still missing a significant percentage of the medium-sized ones, those in the 100 to 500 meter range. These are the city killers, capable of wiping out an entire continent, and we have only catalogued a tiny fraction of the smaller ones, which can still cause immense regional damage, as the Chelyabinsk event demonstrated. The blind spot caused by the Sun is a persistent vulnerability, allowing asteroids to approach undetected from that direction. The recent launch of the NEO Surveyor mission is a step in the right direction, as it will use infrared sensors to find asteroids based on their heat signature. But it is just one telescope. We need a network of such telescopes in space and on the ground, constantly scanning the sky to provide the decades of warning we require. The process from detection to deflection is not instantaneous. It takes time. First, A new asteroid detection must be verified through follow-up observations to refine its orbit. This can take weeks or months. Then, if it is deemed a threat, a mission must be planned. This involves designing a spacecraft, which can take years. Then, the spacecraft must be built and tested, which adds more years. Then, it must be launched and travel to the asteroid, which can take additional years depending on the orbital dynamics. All of this must happen before the asteroid is too close for a gentle deflection to work. This multi-year pipeline means that a threat discovered with only a 5-year warning might be impossible to stop with any method other than a last-ditch nuclear option. This is why the "find them early" mantra is repeated so often by planetary defense experts. It is the cornerstone of any viable strategy. The psychological aspect of time is also critical. Governments and the public are bad at responding to slow-moving, long-term threats. It is easy to ignore a problem that might not manifest for a century. This complacency is our greatest enemy in the race against time. We must shift our thinking from reactive to proactive. We need to invest in the detection infrastructure now, not when we have a specific asteroid in our sights. Every year we delay in building a comprehensive survey is a year of warning time we lose for a future threat. The good news is that the technology for early detection exists. It is primarily a matter of political will and funding. By investing in telescopes like NEO, Surveyor, and supporting ground-based surveys, we are buying ourselves the most valuable commodity in planetary defense: time. With sufficient time, we can use safe, controlled methods. Without it, we are left with desperate, high-risk gambles. The cosmic clock is ticking, and every moment we spend debating or delaying is a moment of precious warning time slipping away. The race is not against the asteroid itself, but against our own inertia and short-sightedness. We have the knowledge to protect ourselves, but we must grant ourselves the time to use it effectively. This means making a sustained, global commitment to finding every potentially hazardous object in our neighbourhood, cataloguing its orbit, and monitoring it for changes. It is a monumental task, but it is the only way to ensure that when we finally build that expensive deflection system, we will have the time needed to use it. The link between detection and deflection is unbreakable. One is useless without the other. So, as we consider the immense costs and technological hurdles, we must remember that the foundation of it all is time. Without decades of warning, all our efforts are for nothing. The cosmic clock does not care about our budgets or our political disputes. It ticks relentlessly onward. Our job is to listen to its ticks by watching the skies, so that we are never caught in a situation where time has run out. The future of our civilization may one day depend on how well we use the time we had today to prepare. This makes the ongoing work of astronomers and the funding of survey missions not just a scientific pursuit, but the most critical insurance policy humanity can possibly purchase. It is a policy that pays out in the most valuable currency of all: the time to act, the time to deflect, and the time to survive. Let us ensure we invest in it generously, for the sake of every generation to come. The challenge is immense, but the alternative is unthinkable. We must become a species that plans for the long term, that looks to the horizon and acts before the storm is upon us. The race against the cosmic clock is one we cannot afford to lose. And it starts with a simple period. Decisive step. Look up, and look early. So, we have the telescopes scanning the skies, giving us that all-important decades-long head start. And we have the theoretical blueprints for deflection technology. But all of that advanced preparation hinges on one colossal, non-technical variable: whether humanity can actually unite and work together. This is the grand, messy, and profoundly human challenge of international coordination. An asteroid hurtling toward Earth is the ultimate global problem. It does not discriminate between nations, ideologies, or economies. Its potential impact zone is the entire planet, and therefore, any effective response cannot be the project of a single nation or a small coalition. It demands a level of unprecedented global cooperation that pushes against the very grain of human history and our current political realities. The first, and perhaps most fundamental, requirement is open and immediate data sharing. For our trajectory models to be accurate, we need observations from every capable telescope on Earth and in space, from every country and every organization. This means that the United States, Russia, China, the European Union, Japan, India, and many others must all be willing to stream their detection data into a common accessible pool in real time. But in a world where data is power and often tied to national security, this is a monumental ask. Consider that some of the most sensitive tracking data might come from military satellites designed to monitor missile launches. Would a nation be willing to declassify and share that information freely, potentially revealing its surveillance capabilities, for the sake of a threat that might be decades away? The instinct for secrecy and strategic advantage is a powerful force to overcome. Building the trust necessary for this level of transparency would require a new paradigm of international relations, one built around the shared vulnerability of our species. This is not just about signing a treaty. It is about fostering a cultural shift among scientists, militaries, and governments to prioritize planetary security over national secrecy. Then comes the even more daunting hurdle: decision-making. Once a credible threat is identified and confirmed, who has the authority to decide on a course of action? Who gives the final go-ahead to launch a multi-billion-dollar deflection mission? The most obvious forum is the United Nations, specifically the Security Council. But its structure, with the veto power held by 5 permanent members, is a recipe for potential paralysis. Imagine a scenario where a deflection plan is proposed, but one permanent member vetoes it due to unrelated geopolitical tensions, a trade dispute, or simply as a bargaining chip. The world would be held hostage to politics while a literal asteroid approaches. Alternatively, perhaps decision-making power should be vested in a new, specially created international body, perhaps a planetary defense coordination organization governed by a council of scientists and engineers. But then, how are these experts selected? Is it one vote per nation, which could give disproportionate influence to smaller countries? Or is it weighted by technological contribution, which would cement the power of spacefaring nations? Either model risks alienation and distrust. The nations providing the bulk of the funding and technology might resist ceding control to a body where they do not have a dominant voice, while smaller nations would rightly fear that their interests could be sacrificed if the deflection strategy inadvertently shifts the risk. For example, a calculated deflection might ensure the asteroid misses the northern hemisphere but increases the probability, however slight, of a future impact in the southern hemisphere. How do you get global agreement on a plan that inherently carries distributed albeit minimized, risks? The question of who literally pushes the button is equally fraught. The actual execution of a deflection mission, especially one involving a kinetic impactor or the immensely controversial nuclear option, would likely be carried out by the entity with the most advanced space capabilities. Would the United States or China be willing to launch such a mission on the orders of an international committee? Would their military and space agencies accept external command? Conversely, Would the rest of the world be comfortable with a single nation possessing and controlling the means to alter the celestial environment? With all the unforeseen consequences that could entail, this concentrates an immense and terrifying power in very few hands, evoking fears of space-based domination disguised as planetary defense. The financial burden, as we have discussed, is astronomical, and its distribution is a diplomatic minefield. Agreeing on a funding formula is a political nightmare. Should it be based on gross domestic product, which would see the United States and China paying the most? Should it be per capita, which would burden populous nations like India? Or should it be based on historical responsibility for carbon emissions, a model that would be fiercely contested? The negotiations would mirror the intractable debates seen in climate change forums, where national self-interest consistently stalls meaningful progress. The difference is that with an asteroid, the consequence of inaction is not a slow-moving crisis, but a sudden, definitive end. Yet, the human psychology of low probability. High-consequence events works against us. It is difficult to maintain political will and financial commitment for a threat that feels abstract and distant. A politician in any country will find it hard to justify allocating billions to an asteroid shield when their constituents are demanding solutions for healthcare, education, and infrastructure. This is where leadership and vision are critical. We need leaders who can articulate planetary defense not as a discretionary expense, but as a fundamental, non-negotiable insurance policy for all of human civilization. The precedent of international cooperation in space, such as the International Space Station, offers a glimmer of hope. It shows that even amid terrestrial conflicts, nations can collaborate on monumental engineering projects in space. However, the ISS operates on a relatively small scale of partnership and has still faced moments of political strain. A planetary defense system would need to be infinitely more robust, with protocols that are resilient to changes in government, economic downturns, and even international conflicts. We cannot allow a war on Earth to disable the very system designed to protect it from space. The development of these protocols needs to start now, long before a specific threat is identified. We need international treaties that clearly define data-sharing obligations, establish a legitimate decision-making body, and outline the chain of command for execution. This will require years of difficult diplomacy, compromise, and confidence-building measures. It means creating joint simulation exercises where nations practice responding to a fictional asteroid threat, working through the data analysis, the political deliberations, and the launch authorization processes. These exercises would reveal the friction points and allow us to design systems to overcome them. In the end, the challenge of international coordination is a test of our evolutionary maturity. Are we a species forever doomed to tribalism and short-sightedness? Or can we evolve to recognize a common destiny and act collectively to secure it? The technology to detect and deflect an asteroid is within our grasp, but the social and political technology to wield it collectively is still under development. The asteroids are coming. It is only a matter of time. Our survival may one day depend not on the brilliance of our engineers, but on the wisdom of our diplomats and the courage of our global citizens to demand cooperation over conflict. The clock is ticking on this front as well, and every day we delay building these essential international frameworks is a day we gamble with our future. Let us not be remembered as the generation that had the knowledge to save the world but lacked the unity to do so. The stars may hold dangers, but history suggests our greatest enemy might be ourselves. Overcoming that enemy is the first and most important step in building a true planetary defense. This journey requires us to build bridges where walls have long stood, to share secrets for the common good, and to trust each other with the very survival of our species. It is a daunting task, but the alternative is unthinkable. We must begin this work today, with the same urgency we apply to the technological challenges, for without global unity, all our other efforts are ultimately futile. The sky does not belong to one nation. It belongs to all of us, and protecting it must be our shared responsibility. This is the final, and perhaps most difficult, frontier in securing our place in the cosmos. But even if we achieve that elusive global unity and perfect international coordination, we are still faced with a Herculean engineering challenge that makes building a skyscraper or a space station look simple by comparison. We are not building a single device or a lone spacecraft. We are constructing what engineers call a system of systems, a vast, interconnected network where every component must work in perfect, flawless harmony. Imagine trying to conduct a symphony orchestra where the musicians are spread across different continents, playing different instruments made by different companies, and all reading from a sheet of music that is constantly being rewritten. That is the scale of complexity involved in creating a functional asteroid defense shield. The individual pieces of this system are impressive on their own. We have the detection layer, a global network of ground-based telescopes like the Vera-C Rubin Observatory, combined with space-based infrared telescopes like the planned NEO Surveyor, all constantly scanning the heavens for new threats and tracking known ones. This detection network feeds a torrent of raw data into the second critical system, the data processing and orbital computation centers. These are not ordinary server farms. They are facilities running incredibly complex simulation software that must account for the gravitational pull of every major body in the solar system, the subtle nudge of the Yarkovsky effect, and the inherent uncertainty in initial observations to calculate and constantly refine the future paths of millions of objects. This processed intelligence then flows into the decision-making framework, the political and command layer we just discussed, where international bodies must assess the risk and authorize a response. Once a decision is made, the action layer springs into life. This involves the deflection technologies themselves, the kinetic impactor spacecraft sitting in storage, the designs for gravity tractors, and the launch infrastructure needed to send them on their way. We are talking about heavy lift rockets, launch pads, and mission control centers, all kept in a state of readiness. Finally, there is the communication backbone that ties it all together, a resilient network of satellites and ground stations that must relay data, commands, and status updates between all the other layers without a single dropped packet or moment of downtime. The monumental challenge is making all these disparate systems, often developed by different countries, different companies, and different engineering cultures, work together as one. This is the problem of integration. It is not enough for each part to be brilliant individually. They must be seamlessly compatible. The data format from a Japanese telescope must be instantly readable by an American orbital simulation program. The command protocol for a European deflection spacecraft must be understood by a Russian launch vehicle's interface. The software that models asteroid trajectories must be able to communicate its findings clearly and unambiguously to the international decision-making body. Any incompatibility, any minor bug in the data translation, any miscommunication between systems could introduce a fatal error. This requires an unprecedented level of international standardization. We would need global agreements on data protocols, communication frequencies, software interfaces, and engineering specifications. It is a diplomatic effort as much as a technical one. The reliability of the entire system is only as strong as its weakest link. If one key telescope in the network goes offline for maintenance at the wrong time, we might miss a crucial observation that refines an asteroid's trajectory from a miss to a hit. If a software update in the data processing center introduces a glitch that miscalculates orbits, it could trigger a false alarm or, worse, cause us to miss a real threat. If a communication satellite fails, it could blind a mission control center at the critical moment of launch. The system must be designed with redundancy at every level. We need backup telescopes, backup data centers, backup communication channels, and even backup deflection spacecraft. This redundancy multiplies the cost and complexity exponentially. But it is non-negotiable for something as critical as planetary defense. Furthermore, the system cannot be static. It must be adaptable and upgradable over time. New telescope technology will emerge, more powerful computers will be developed, and more efficient deflection methods will be invented. The system of systems must be designed to incorporate these improvements without causing a total breakdown or requiring a complete overhaul. This is like trying to upgrade the engine of a car while it is speeding down the highway. The integration challenge also extends to testing. We cannot wait for a real asteroid threat to see if the entire system works. We need to run large-scale simulations and drills that involve all components. These would be planetary defense wargames, where a fictional asteroid is discovered. Its trajectory is tracked by the real telescope network. The data is processed by the real computation centers. The international body practices its decision-making under simulated pressure. And a mock deflection mission is planned and executed up to the point of launch. These exercises would reveal the friction points, the software bugs, and the procedural failures that must be ironed out before a real crisis. The human element is just as critical as the technological one. The engineers operating the telescopes, the scientists interpreting the data, the diplomats making the decisions, and the flight controllers launching the spacecraft all need to be trained to work together as a single, cohesive unit. They need shared procedures, common terminology, and a deep trust in each other's competence. This requires joint training programs and international exchanges to build a shared culture of planetary defense. The timeline for action adds another layer of integration complexity. The process from detection to deflection is a long chain of events, and each step must dovetail perfectly with the next. The detection must happen early enough to allow time for trajectory refinement, which must be completed in time for the decision-making body to deliberate, which must reach a conclusion in time for the spacecraft to be launched and to rendezvous with the asteroid while it is still far enough away for a gentle deflection to work. A delay in any one step, whether from a technical glitch, a political debate, or a launch failure, can compress the timeline for the subsequent steps, potentially forcing us into riskier last resort options. This intricate dance requires a master clock and a synchronized schedule that all participating nations and agencies adhere to religiously. The financial cost of building and maintaining this integrated system is, as we have seen, astronomical, but the cost of poor integration could be infinitely higher, a catastrophic failure when we need it most. Therefore, the engineering of this system of systems is not just about connecting wires and writing software. It is about building the most reliable, resilient, and interoperable machine humanity has ever conceived. It is a testament to our ability to think and act on a civilization-wide scale, to weave together our best technologies and our brightest minds into a shield that can protect our entire world. The key to making it work is not a technological breakthrough in rocketry or telescopes, but a relentless focus on integration, on making sure that every single part, from the largest telescope mirror to the smallest line of code, is working in concert toward the common goal. Without this seamless integration, we have a collection of impressive but disconnected parts. With it, we have a fighting chance against the randomness of the cosmos. This is the final, intricate puzzle piece that must be snapped into place for planetary defense to become a reality. It requires patience, precision, and an unwavering commitment to getting the details right. For in a system this complex, the devil is truly in the details, and the stakes could not be higher. The journey to build this integrated shield is long, but every step toward better coordination between systems is a step toward a safer future for everyone on Earth. But even if we somehow master the immense technical and political challenges of building this perfectly integrated global defense network, we are immediately confronted with a deeply human and psychological problem that could undermine the entire endeavor: the dilemma of the false alarm. This is the cry wolf effect, a concept from the fable that becomes terrifyingly real when applied to planetary defense. Imagine the scenario. Our sophisticated network of telescopes and computers identifies a new asteroid. Initial orbital calculations, based on limited data, indicate a small but non-zero probability of impact with Earth in 20 years. This triggers a preliminary alert within the scientific community and, inevitably, the information leaks to the public. News outlets blast headlines about a potential asteroid impact. Social media erupts in panic, and governments face a wave of public fear and demand for action. Then, over the following weeks and months, as more observational data pours in, the orbit is refined. The new calculations show that the asteroid will, in fact, miss Earth by a comfortable margin. The threat is downgraded, and the all-clear is given. The immediate crisis is averted, but the long-term damage is done. This is a false alarm, and its consequences can be devastating for future preparedness. The first and most obvious impact is on public trust. When people are scared by a threat that then vanishes, they feel misled. They might become cynical, believing that scientists are either incompetent alarmists or that the entire asteroid threat is exaggerated to secure funding. This erosion of trust makes it incredibly difficult to mobilize public support and political will for the next, potentially real, threat. Why should anyone believe the warning if the last one was a false alarm? This loss of credibility is a poison that can paralyze the entire defense system before it's ever needed. The cry wolf effect forces scientists and officials into an impossible balancing act. On one hand, they have an ethical obligation to be transparent and inform the public about potential risks. Hiding a real threat until absolute certainty is achieved would be irresponsible and could leave no time for action. On the other hand, sounding the alarm too early, based on uncertain data, risks causing widespread panic and destroying public confidence. This creates a pressure to be overly cautious, to wait for more data, to be absolutely sure before saying anything. But in the world of asteroid prediction, absolute certainty often comes only when it is too late to do anything about it. The very nature of orbital mechanics means that early predictions are inherently fuzzy. An asteroid's path is not a single line, but a cloud of possibilities. And it takes time and many observations to shrink that cloud down to a definitive trajectory. During that uncertain period, the responsible agencies are stuck between a rock and a hard place. Do they announce the potential risk and risk a false alarm? Or do they stay quiet and risk being accused of a cover-up if the threat turns out to be real? This dilemma is exacerbated by the modern media landscape. A tentative scientific assessment can be transformed into a definitive apocalyptic headline in minutes, spreading fear globally before scientists have had a chance to complete their analysis. The resulting panic could have real economic and social costs, from stock market volatility to civil unrest. Furthermore, A high-profile false alarm could have severe political repercussions. Governments that allocated emergency resources or made public statements based on the initial alert would face embarrassment and criticism. This could make them hesitant to commit resources or political capital the next time a warning is issued. They might demand an unattainable level of certainty before acting, effectively neutering the early warning system. The scientific community itself could become more risk-averse. Fearing the backlash from another false alarm, researchers might become reluctant to publish preliminary findings or voice concerns until they have ironclad proof. This culture of excessive caution could slow down the vital process of data sharing and collaborative analysis, which is the lifeblood of accurate trajectory prediction. The very speed and openness required for an effective defense could be sacrificed to avoid public relations disasters. This problem is not theoretical. We have seen smaller versions of it with other threats. In the early days of the COVID-19 pandemic, mixed messages and evolving scientific understanding led to public confusion and mistrust in health authorities. For an asteroid impact, the stakes are infinitely higher, and the timeframes are much longer, making it even harder to maintain public engagement and trust over decades. So, how do we manage this? The solution lies in clear, consistent, and calibrated communication from the very beginning. The scientific community needs to establish and publicize a standardized scale for communicating impact risk, similar to the Torino scale or the newer Palermo scale, but designed for public consumption. Every potential threat should be communicated not as a simple yes or no, but as a probability with an associated uncertainty. The public needs to be educated that initial predictions are like a first draft, subject to change as more information comes in. The messaging must emphasize that an elevated risk level is a call for more observation, not a cause for panic. It's a signal to point more telescopes at the object, not to start building bunkers. Transparency about the process and the uncertainties is key. Officials should explain how orbital calculations work, why early data is imperfect, and how the certainty will improve over time. This builds public resilience and understanding instead of fear. Furthermore, the protocols for public alerts must be carefully designed. There should be clear thresholds that trigger different levels of announcement. A low probability event might only be discussed within scientific circles, while a high probability event would warrant a coordinated, global public announcement from a trusted, unified source, such as a United Nations Planetary Defense Office. This avoids the chaos of multiple, conflicting messages from different national agencies. Practice drills and simulations that include communication strategies are essential. We need to test not only our technical response, but also our public messaging under pressure. How do we keep the public informed without causing panic? How do we retract an alert gracefully if it turns out to be false? Building this communication muscle is as important as building the telescopes. Ultimately, overcoming the false alarm dilemma is about building a long-term relationship of trust between the scientific community, governments, and the public. It requires honesty about what we know, what we don't know, and how we are working to reduce the uncertainty. It means accepting that occasional false alarms are an inevitable part of an early warning system designed to save lives, and we must be prepared to manage them without losing public confidence. The cry wolf effect is a powerful psychological force, but it can be mitigated through education, transparency, and carefully crafted communication. If we fail at this, we risk creating a system that is technically perfect but socially and politically unusable, a shield that nobody believes in until it is too late. The goal is to create a society that is informed and vigilant, not panicked and cynical. one that understands that a warning is a call to watch and learn, not a signal of certain doom. This cultural shift is a critical part of planetary defense, ensuring that when a real wolf finally appears at the door, we are ready to listen and act. But even if we perfect our communication to avoid panic and false alarms, we are then forced to confront a much deeper and more profound question that ventures into uncharted ethical territory. What are the moral implications of our actions when we start moving celestial bodies? This is not just a technical problem. It is a philosophical and ethical dilemma on a cosmic scale. When we talk about deflecting an asteroid, we are essentially playing with the gravitational billiards of our solar system, and a miscalculation or an unforeseen consequence could have repercussions that echo for millions of years. The core ethical problem is this: in our desperate and entirely justified attempt to save our own planet, could we inadvertently be condemning another world or even creating a new threat for ourselves in the future? Imagine we successfully nudge a large asteroid away from a collision course with Earth. We celebrate. The crisis is averted, and life on Earth continues. But what if that deflection, that subtle change in velocity, puts the asteroid on a new trajectory that will see it collide with Mars in a few decades? Now, Mars is currently uninhabited by anything we know of, but it is a world of immense scientific value and the potential future home for humanity. A large impact could obliterate unique geological records, destroy potential signs of past or present microbial life, and contaminate the planet with earthly organisms carried on our spacecraft, making it harder to find indigenous Martian life. It could even make future colonization efforts more dangerous by increasing the background impact rate. So, do we have the right to sacrifice Mars to save Earth? Most people would probably say yes without hesitation, but the ethical principle is unsettling. It sets a precedent that our world is more valuable than others, a form of planetary solipsism that could have implications as we expand into the cosmos. The problem becomes even more acute if we consider the possibility of life elsewhere. What if, in the distant future, we discover a simple microbial ecosystem on Europa or Enceladus? Would deflecting an asteroid toward one of those moons to save Earth be an act of interplanetary genocide? These are extreme scenarios, but they force us to think about our responsibilities beyond our own atmosphere. The ethical concerns are not limited to other planets. Our actions could boomerang back to haunt us. Space is a dynamic system, and orbits are complex. An asteroid deflected today might be perturbed by Jupiter's gravity in the future and swung back onto a collision course with Earth a century or a millennium from now. We might be solving a problem for our generation only to create a much worse one for our descendants. Would that be fair? Do we have the right to make such a long-term gamble? This introduces the concept of intergenerational ethics, where actions taken today have consequences for people who have no say in the decision. Furthermore, there is the immediate risk to our own infrastructure in space. Any deflection attempt, especially a kinetic impactor or a nuclear blast, could create a cloud of debris. Some of this debris might be ejected at high velocity, crossing the orbits of satellites and space stations. A single piece of asteroid fragment, even a small one, travelling at orbital speeds could destroy a multi-billion-dollar communications satellite, disrupt global GPS networks, or puncture the International Space Station. We would be creating a new, man-made hazard in low Earth orbit while trying to prevent a natural one. Who is liable for that damage? If a piece of an asteroid we fragmented destroys a satellite belonging to another country, is it an act of war or a tragic accident? The current legal frameworks in space law are not equipped to handle this. The Outer Space Treaty establishes that states are responsible for their national activities in space and liable for damage caused by their space objects. But applying this to a deliberate asteroid deflection operation is murky territory. This leads to the absolute necessity of developing a comprehensive ethical and risk assessment framework for planetary defense. We cannot wait for a crisis to figure this out. We need international agreements, established through bodies like the United Nations, that outline the principles for such actions. These protocols would need to address several key questions. First, what is the threshold of certainty required before we act? How sure do we need to be that the asteroid is a threat? And how sure do we need to be that our deflection will not cause unacceptable collateral damage? Second, how do we weigh the risks? We would need to run sophisticated simulations to model the long-term future of any asteroid we plan to move, calculating the probabilities of it ever impacting another planet or being redirected back to Earth. The calculations would need to span centuries, maybe even millennia, which is a daunting task. Third, who has the authority to make these ethical judgments? Is it a committee of scientists? A panel of international diplomats? A public referendum? This ties back directly to the challenges of international coordination we discussed earlier. The decision cannot be made by a single nation. It must be a global consensus. But achieving that on a matter of such profound ethical weight is incredibly difficult. Different cultures and legal systems have different perspectives on risk, responsibility, and the value of other worlds. Some might argue for a utilitarian approach, the greatest good for the greatest number, which invariably means prioritizing Earth. Others might advocate for a precautionary principle, where we avoid any action that has even a remote chance of causing harm to another celestial body, even if that inaction risks Earth. There is no easy answer. This ethical dimension also affects the choice of deflection technology, a method like a gravity tractor, which slowly pulls an asteroid without contact, is ethically cleaner because it minimizes the risk of creating debris. A kinetic impactor is riskier, and a nuclear option is the most ethically fraught due to the potential for fragmentation and radioactive contamination. Therefore, the ethical assessment might push us towards safer, more controlled methods, even if they are more expensive or require more time. In the end, the ethics of planetary defense force us to grow up as a species. We can no longer think of ourselves as isolated on our planet, acting with impunity. We are becoming active participants in the solar system. And with that power comes immense responsibility. Every time we consider moving a mountain in space, we must ask not only, can we? But also, should we? And what are the consequences for everyone and everything else? Developing this ethical framework is as crucial as developing the rockets and the telescopes. It is about building the wisdom to use our power wisely. We are on the cusp of becoming planetary engineers, and we must ensure that our first forays into this new role are guided by caution, foresight, and a deep respect for the cosmic environment we share. This is not just about saving ourselves today. It is about establishing a legacy of responsible stewardship that will define our place in the universe for generations to come. The choices we make now will set a precedent for how humanity interacts with the cosmos. And we must strive to make those choices with both intelligence and compassion, ensuring that our survival does not come at an unacceptable cost to the rest of the solar system. The journey is as much about discovering our ethical boundaries as it is about pushing our technological ones. As we navigate these complex ethical questions about our role in the solar system, it naturally leads some people to propose a seemingly elegant way to sidestep the entire problem. Why not just abandon the idea of a planetary shield and instead focus on becoming a multi-planetary species by colonizing Mars? This is often touted as the ultimate Plan B, a backup for humanity in case something goes horribly wrong on Earth. It sounds like a visionary escape hatch, a way to ensure the survival of our species no matter what happens here. But when you scrutinize this idea closely, especially in the context of planetary defense against asteroids, it reveals itself as a dangerous and ultimately fallacious solution. The core of the fallacy lies in a fundamental misunderstanding of what a Martian colony would actually be and what it could withstand. Let's be clear. Establishing a self-sustaining city on Mars is an incredibly noble and ambitious goal, one that would drive technological innovation and expand human horizons. But to present it as a viable insurance policy against a global catastrophe on Earth, particularly an asteroid impact, is to ignore the brutal realities of Martian environment and the profound dependence any early colony would have on its home planet. Imagine a large asteroid, one capable of causing a mass extinction event, strikes Earth. The immediate effects are devastating. Tsunamis, firestorms, and a thick layer of dust and ash thrown into the atmosphere, triggering a prolonged impact winter that cripples agriculture and collapses ecosystems worldwide. Now, picture a small, fledgling colony on Mars at that moment. What would its fate be? Contrary to the sci-fi fantasy, it would not be a safe haven. It would almost certainly be a death trap. The colony would be entirely dependent on Earth for its survival. It would need a constant resupply of advanced technology, spare parts, medical supplies, genetic material for agriculture, and likely even key personnel. The industrial and technological base required to be truly self-sufficient, to mine resources, manufacture complex electronics, and produce everything from pharmaceuticals to advanced alloys is something that would take centuries to develop on Mars. With Earth's civilization in ruins, that lifeline is severed. The colony would be like a newborn baby whose mother has suddenly vanished. It might survive for a short while, but its long-term prospects are grim. It would slowly wither as systems failed, spare parts ran out, and the delicate balance of its closed-loop life support systems was disrupted. Furthermore, the notion that Mars itself would be a safe refuge is flawed. Mars is an incredibly hostile world. It has an atmosphere about 1% as thick as Earth's, offering virtually no protection from cosmic radiation or solar flares. Its lack of a global magnetic field means that the surface is bombarded by high-energy particles that would be harmful to human health over the long term and could damage electronics. An asteroid impact on Earth might also have indirect effects on Mars. While the physical impact wouldn't reach Mars, the societal collapse on Earth would. The global economic and technological infrastructure that enables spaceflight would be destroyed. The companies, governments, and international collaborations that launched and supplied the Martian colony would cease to exist. There would be no more rockets launching from Cape Canaveral or Baikonur. The colony would be utterly alone, stranded millions of miles away with no hope of rescue or reinforcement. Even if the colony were somehow magically self-sufficient from day one, which is a physical impossibility with current or foreseeable technology, it would still be vulnerable. A large asteroid impact on Earth is a planet-wide event that could throw enough debris into space to increase the impact risk throughout the inner solar system for a time. But more importantly, the psychological and cultural blow would be immense. The colonists would be the last remnants of a dead civilization, living in a desperate struggle for survival on a barren world, with the knowledge that their entire home, their history, and the billions of people they knew are gone. This is not a backup. It is a tragedy of unimaginable scale. The Plan B argument also creates a perverse incentive. It can be used as a justification for inaction on Earth. Why spend trillions on a complex asteroid shield when we can just go to Mars? This line of thinking is dangerously short-sighted. It treats a Martian colony as a disposable concept, a secondary project, when in reality, making humanity a multiplanetary species is a goal that requires a healthy, thriving, and technologically advanced Earth to achieve and sustain for generations. We cannot run away from our problems on Earth. We must solve them here. Investing in planetary defense is not an either-or proposition against space exploration. In fact, the two are deeply complementary. The technology we develop for deflecting asteroids, advanced propulsion, autonomous navigation, in situ resource utilization is the very same technology that would be essential for building and maintaining a sustainable presence on Mars. But the primary goal must always be to protect our home planet first. Earth is, and will remain for the foreseeable future, the only planet perfectly suited for human life. It has a thick atmosphere, a protective magnetic field, abundant liquid water, and a complex biosphere that supports us. No sealed habitat on Mars can ever replicate the richness and resilience of Earth's natural environment. The resources required to make Mars even marginally habitable on a large scale are astronomical, and it would be far easier and more effective to use those same resources to fix the problems we have here, including defending against asteroid impacts. The fallacy of the Martian Plan B is ultimately a failure of imagination in the wrong direction. It imagines a spectacular escape to another world, but fails to imagine the hard, meticulous work required to safeguard the world we have. It is a seductive narrative, but it is a distraction from the immediate and solvable challenge of planetary defense. Our priority should be to become guardians of Earth, not refugees from it, by focusing our efforts on detection, deflection, and international cooperation. We are making a direct investment in the long-term survival of human civilization on its home planet. This doesn't mean we should abandon dreams of Mars. It means we should pursue them for the right reasons, for science, for exploration, and for the expansion of human knowledge, not as a hastily conceived escape plan from responsibilities we are unwilling to face. The path to a true multiplanetary future runs through a secure and thriving Earth. Let's not put the cart before the horse. Ensuring that Earth remains a safe harbour is the foundational step upon which all other spacefaring ambitions must be built. The idea of using Mars as a backup is not just impractical, it is a profound misunderstanding of our situation. We are children of Earth, and our first duty is to protect our cradle. The challenge of planetary defence is a test of our maturity as a species, and passing that test means rejecting easy outs and committing to the hard, necessary work of protecting our only home. This commitment will, in turn, provide the stability and technological base that will eventually allow us to reach out to the stars not as fleeing refugees, but as confident explorers. So, while the red planet beckons with its own mysteries and promises, let us remember that the blue planet is where our heart is, and its defense is the most important mission we will ever undertake. The future of humanity depends on it. However, committing to that hard work is easier said than done, because we're up against a powerful internal enemy, our own psychology. The human brain is notoriously bad at evaluating risks that have a very low probability of happening, but would have catastrophic consequences if they did. This mental blind spot is perhaps the single greatest obstacle to building a planetary defense system, because it affects everyone from the average citizen to the highest levels of government. Think about it. How often do you worry about being struck by lightning? Probably almost never, because the odds are incredibly low. Now, how often do you worry about a giant asteroid hitting Earth? For most people, the answer is the same. It just doesn't feel real or imminent. This isn't a character flaw. It's a feature of how our brains evolved. We're wired to respond to immediate, visible threats like a predator lurking in the bushes or a car swerving toward us. Our ancestors didn't need to worry about events that might happen once every million years. They needed to focus on dangers that were present and actionable right now. This evolutionary baggage means that when we hear about an asteroid impact that might occur in 50 or 100 years, our brain instinctively files it under not my problem or even science fiction. This psychological phenomenon is often called probability neglect. We tend to either ignore very low probability events entirely or, if we do think about them, we overreact emotionally because the outcome is so terrifying. But in the case of asteroids, the sheer distance in time makes it easy to dismiss. The statistics are clear, large. Civilization-ending impacts are incredibly rare, occurring on timescales of millions of years. But that doesn't mean the risk is zero, and the consequences are so ultimate that even a tiny probability demands attention. Yet, because no one alive today has experienced such an event, and because it hasn't happened in recorded history, it feels abstract and unreal. This is compounded by the availability heuristic, a mental shortcut where we judge the likelihood of an event based on how easily examples come to mind. Can you recall the last time an asteroid caused major damage? The Chelyabinsk event in 2013 might come to mind. But that was a relatively small rock that injured people and damaged property without causing mass casualties. For most, it's a distant news story, not a personal memory. Compare that to the immediacy of a hurricane, a pandemic, or an economic crisis. These are threats we can visualize and feel, so they command our attention and resources. This cognitive bias leads to a collective complacency that is incredibly difficult to shake. Politicians, who are often focused on short-term election cycles, find it hard to justify allocating billions of dollars to a problem that might not materialize for centuries. Why spend on asteroid defense when there are pressing issues like healthcare, education, and infrastructure that voters care about right now? This creates a vicious cycle. Without public pressure, there's no political will. Without political will, there's no funding. Without funding, we can't build the necessary systems. The problem is also exacerbated by optimism bias, where people believe that bad things are less likely to happen to them than to others. We think, it won't happen to us. Or scientists will figure something out if it ever gets close. This overconfidence in our ability to handle a crisis at the last minute is dangerously misplaced when dealing with asteroids, where last-minute solutions are often impossible or highly risky. The psychology of low-probability threats also affects how the media covers the issue. When a potential asteroid is discovered, initial reports might sensationalize the risk to grab attention. But if subsequent observations show it's not a threat, the story disappears, leaving the public with the impression that it was a false alarm or hype. This cry wolf effect, which we touched on earlier, further erodes trust and makes people even more skeptical the next time a warning is issued. So, how do we overcome this deep-seated psychological barrier? The first step is awareness, simply understanding that our brains are tricking us into inaction. Education is crucial. We need to reframe the asteroid threat not as a speculative doom scenario, but as a manageable risk, similar to how we view other large-scale insurance policies. No one expects their house to burn down, but we buy home insurance because the consequences would be devastating. Planetary defense is insurance for our entire civilization. We can make the risk more tangible by using analogies that people can relate to. For instance, the odds of a large asteroid impact in your lifetime might be similar to the odds of dying in a plane crash, very low. But we still take precautions like wearing seatbelts and having safety regulations. Another strategy is to emphasize the technological spin-offs and benefits of investing in planetary defense. The research and development required for asteroid detection and deflection can lead to advancements in space travel, robotics, and materials science that have everyday applications, creating jobs and driving innovation. This makes the investment feel more immediate and worthwhile. Storytelling and visualization can also help. Instead of just quoting probabilities, we can use simulations and virtual reality to show what an impact would actually look and feel like, making the abstract concrete. Missions like DART, which successfully demonstrated a kinetic impact, provide tangible proof that we can do something about the threat, which helps combat feelings of helplessness. International collaboration can also play a role in shifting psychology. When multiple countries work together on a shared goal, it reinforces the idea that this is a global priority, not just a niche scientific concern. Public figures and influencers can help by talking about the issue in relatable terms, stressing that protecting Earth is a universal human value that transcends politics. Ultimately, overcoming the psychology of low-probability threats requires a cultural shift. We need to cultivate a long-term perspective that values future generations and recognizes that some risks, however rare, are worth preparing for simply because the stakes are too high to ignore. This isn't about living in fear. It's about acting with wisdom and foresight, by acknowledging our psychological biases and actively working to counter them. We can build the public and political support needed to fund and develop a robust planetary defense system. The journey to safeguard our planet is as much about winning the battle in our minds as it is about winning the battle in space. Let's not allow our hardwired instincts to be the reason we fail to protect our home. The time to act is now, while the sky is still clear. Because waiting for a threat to feel real might mean waiting until it's too late. This psychological hurdle is the quietest yet most pervasive challenge we face, and conquering it is essential for turning the dream of a shielded Earth into a reality. Every step we take to educate, communicate, and motivate brings us closer to that goal, ensuring that we don't become victims of our own cognitive limitations. The future of humanity depends on our ability to think beyond the immediate and embrace our role as stewards of the planet, ready to defend it against all odds, no matter how remote they may seem. So, we have managed to overcome the psychological hurdles and the complacency that makes it so hard to fund and support planetary defense. And we are finally building that global shield. But here is the cruel irony. The very system designed to protect us is itself incredibly vulnerable, because it depends entirely on a fragile network of assets we have placed in space. This is the classic problem of putting all your eggs in one basket. But in this case, the basket is orbiting Earth at 17,000 miles per hour, and it is filled with our eyes, ears, and voices in the cosmos. Our planetary defense strategy is not a standalone weapon. It is a complex dance that relies on a delicate web of space-based infrastructure. And if that web is torn, the entire defense collapses before the first asteroid even gets close. Let us break down what this infrastructure actually does. First, you have the detection layer. This includes space telescopes like the planned NEO Surveyor, which will orbit at a Lagrange point to scan the skies in infrared, finding asteroids that are too dark for ground-based telescopes to see. But it is not just one telescope. It is a constellation of eyes in the sky, working in tandem with observatories on Earth. Then, you have the communication backbone. Once a potential threat is detected, the data needs to be relayed across the globe instantly. This is done through a network of communication satellites. Commands to track the object, instructions to refine its orbit, and eventually, the order to launch a deflection mission all travel through these satellites. Without them, the left hand would not know what the right hand is doing. Next, consider the navigation layer, the Global Positioning System, or GPS, is a constellation of satellites that provides precise timing and location data. This is not just for your phone to find the nearest coffee shop, it is critical for launching rockets. The trajectory of a deflection spacecraft must be calculated with insane precision, and that requires GPS data to know the exact position of the launch pad and the initial path of the rocket. During the mission, navigation satellites help track the spacecraft's position as it journeys millions of miles to intercept the asteroid. Now, imagine if any part of this infrastructure fails. The threats to these space assets are numerous and growing. The most obvious one is space debris. We have littered Earth's orbit with millions of pieces of junk, from defunct satellites to spent rocket stages and even tiny flakes of paint. Each piece is travelling at orbital velocities, meaning a collision with even a small object can release the energy of a hand grenade, instantly destroying a critical satellite. There have already been close calls and actual collisions. In 2009, a defunct Russian satellite collided with an active Iridium communications satellite, creating thousands of new pieces of debris. If a similar collision were to take out a key telescope or a communications satellite during an asteroid crisis, we could lose our ability to track the threat accurately. The data flow would be disrupted, and our response would be delayed or based on outdated information. Then there is the threat of intentional attacks. Anti-satellite weapons, or ASATs, have been tested by several nations, including the United States, China, Russia, and India. These tests deliberately destroy satellites, creating massive debris clouds that pose a long-term hazard to everything in orbit. In a tense geopolitical situation, an adversary might see disabling planetary defense assets as a strategic move. If the communication satellites are taken out, we cannot coordinate a global response. If the tracking telescopes are blinded, we cannot monitor the asteroid's path. This is not science fiction. It is a real and present danger. The vulnerability extends to cyber attacks. Satellites are controlled from the ground, and those control systems are connected to networks that can be hacked. A skilled hacker could potentially take control of a satellite, disable it, or feed it false data during the DART mission. For example, if the communication links had been compromised, the spacecraft might have missed its target entirely. The consequences of such an attack during a real deflection attempt would be catastrophic. We must also consider natural threats. Space weather, such as solar flares and coronal mass ejections, can unleash waves of charged particles that overwhelm satellite electronics, causing permanent damage. A major solar storm, like the Carrington event of 1859, if it happened today, could knock out a significant portion of our satellites, crippling communication, navigation, and detection capabilities for days, weeks, or even months. In the context of planetary defense, where timing is everything, such an outage could be fatal. The dependency does not end in space. The data from all these satellites is processed on Earth in data centers that rely on stable power grids and internet connectivity. These terrestrial systems are themselves vulnerable to attacks, natural disasters, or even simple human error. A power outage in a key data center could halt the orbital calculations needed to refine an asteroid's trajectory. This interconnectedness means that a failure in one part of the system can cascade into a total system collapse. So, what can we do about it? Protecting the protectors must become a central pillar of planetary defense. This means investing in the resilience of our space infrastructure. We need to design satellites with better shielding against debris and radiation. We need to build redundancy into the system so that if one satellite fails, others can immediately take over its functions. Constellation designs, where multiple smaller satellites work together, are more robust than relying on a few large, vulnerable assets. We also need improved space situational awareness. This involves tracking debris more accurately so we can maneuver satellites out of harm's way when a collision is predicted. Projects like the Space Fence, a radar system that tracks smaller debris, are steps in the right direction. But we need global cooperation to make this data available to all. Active debris removal missions, which aim to clean up the worst of the junk, are also crucial, though they are still in early stages of development. On the security front, we need international agreements to protect critical space assets, especially those used for planetary defense, just as hospitals are considered neutral ground in conflicts. Perhaps we can establish similar protections for satellites that serve global safety functions. This would require new treaties or amendments to existing ones like the Outer Space Treaty. Cybersecurity for space systems must be prioritized, with hardened encryption and secure communication channels to prevent hacking. Furthermore, we need to diversify our capabilities. While space-based assets are invaluable, we should also strengthen ground-based telescopes and develop alternative communication methods that are less reliant on satellites. Having multiple, independent ways to detect threats and coordinate responses reduces the risk of a single point of failure. The development of rapid launch capabilities is also key. If a critical satellite is destroyed, we need to be able to replace it quickly. Companies like SpaceX are working on reusable rockets that could make responsive launches more feasible. But we need the infrastructure and pre-positioned assets to make this a reality for defense purposes. In essence, building a planetary defense system is not just about the deflection technology. It is about creating a resilient dot, survivable, and secure support network. We are building a chain, and every link from the telescope in orbit to the data center on the ground must be strong. A broken link at the wrong moment could mean the difference between a successful deflection and a global catastrophe. This is why the conversation about planetary defense must include space infrastructure protection. We cannot assume that the space environment will remain benign or that our assets will be safe from harm. We must proactively defend the defenders. As we look to the future, the security of Earth depends not only on pushing asteroids away, but also on preserving the capabilities that allow us to see them coming and to act. It is a dual challenge. Watch the skies and guard the watchers. Let us not build a magnificent shield only to find that the handle is made of glass. The effort to secure our space infrastructure is a critical investment in our own survival, ensuring that when the time comes, we are not left blind, deaf, and mute in the face of danger. This is the unsung hero of planetary defense, the silent guardian that must itself be guarded with vigilance and determination. The journey to protect Earth is far from over, and securing our orbital assets is the next logical and essential step on that path. But even if we successfully fortify our orbital infrastructure against debris, attacks, and solar storms, we are immediately confronted with the raw, physical reality of the energy required to actually move a celestial object. This isn't about swatting a small rock. It's about shifting the trajectory of a mountain-sized mass traveling at hypersonic speeds. And the numbers involved are so vast, they defy everyday comprehension. Let's start with a simple but shocking fact. To change the velocity of a large asteroid by just 1 centimeter per second, a change so small it's almost imperceptible, we need to apply a colossal amount of energy. This is because of the basic physics of momentum. The asteroid's mass is so immense that even a tiny change in its speed requires a huge impulse. For an asteroid 1 kilometre in diameter, which is well within the range of city-killing or even continent-killing objects, achieving that minuscule 1 centimetre per second velocity change could require an energy release equivalent to several modern nuclear bombs. We are not talking about a single firecracker. We are talking about the combined energy of multiple Hiroshima-sized explosions, all focused into a precise nudge. This scale is what separates a controlled deflection from a chaotic destruction. The successful DART mission was a brilliant proof of concept, but it was essentially a test on a very small scale. DART impacted a moonlet called Dimorphos, which was only about 160 meters across, orbiting a larger asteroid. The impact was designed to change the moonlet's orbit around its parent body, and it succeeded beautifully, altering its orbital period by several minutes. But that moonlet was a tiny target compared to the asteroids we truly fear. Scaling up from that demonstration to a genuine planetary defense scenario against a kilometer-sized object is not a linear process. It's an exponential leap in difficulty. The energy required doesn't just double when the asteroid's mass doubles. It increases by orders of magnitude. A 1 kilometer asteroid isn't 10 times more massive than a 100-meter asteroid. It's closer to 1,000 times more massive, because mass scales with the cube of the diameter. So, the gentle push that worked for DART would be utterly insignificant against a larger threat. It would be like trying to stop a speeding freight train by throwing a pebble at it. To deflect a truly dangerous asteroid, we would need a much more powerful impact. This could mean building a kinetic impactor spacecraft that is itself massively larger and heavier, perhaps weighing many tons, and accelerating it to even higher speeds to deliver a more powerful punch. But there are physical and practical limits to how big and fast we can make a single spacecraft with current rocket technology. Alternatively, we could opt for multiple impacts, sending a swarm of smaller impactors to strike the asteroid in sequence, each one adding a little bit of velocity change over time. This would be like tapping a billiard ball repeatedly to slowly guide it rather than trying to hit it with one mighty strike. However, this approach requires exquisite coordination and a lot of time, which we might not have if the asteroid is discovered late. Then there is the nuclear option, which we've discussed, as it represents the most concentrated form of energy we can currently envision deploying. A standoff nuclear detonation could, in theory, provide the immense energy needed to vaporize surface material and create a thrusting jet. But it comes with all the political, legal, and fragmentation risks we already covered. The core engineering challenge here is not just about having a lot of energy. It's about generating, storing, and deploying that energy in the vacuum of space in a controlled and precise manner. On Earth, we have infrastructure for large energy projects, power plants, grids, fuel depots. In space, everything must be self-contained, reliable, and capable of operating autonomously millions of miles from help. Generating the energy for a deflection mission could involve massive solar arrays, but solar power diminishes with distance from the sun and might not provide the quick, intense burst needed for an impact. Nuclear reactors on spacecraft are a possibility, but they are complex, heavily regulated, and present their own safety concerns during launch and operation. Storing that energy is another hurdle. Chemical propellants, like those used in rockets, have a limited energy density. To carry enough fuel for a high-energy impact or a prolonged gravity tractor mission, we would need enormous fuel tanks, making the spacecraft heavier and more expensive to launch. Ion thrusters are more efficient but provide very low thrust, making them suitable only for missions with decades of lead time. Deploying the energy precisely is the final and most critical step. For a kinetic impactor, the energy is deployed in a split second at the moment of collision. The spacecraft must hit the exact right spot on the asteroid to maximize momentum transfer. Hitting a irregularly shaped, rotating object at a precise point while both are moving at incredible speeds is a navigation nightmare. For a gravity tractor, the energy deployment is slow and steady, requiring the spacecraft to maintain a perfectly stable position relative to the asteroid for years, fighting against subtle gravitational perturbations and solar radiation pressure. Any drift could reduce the effectiveness or even cause a collision. The sheer scale of this energy problem means that deflecting an asteroid is one of the greatest engineering challenges ever conceived. It pushes the boundaries of material science, propulsion technology, and autonomous guidance. We are essentially talking about building a machine that can unleash the energy of a natural disaster in a controlled direction, on command, in the most hostile environment imaginable. This is why ongoing research and development are so crucial. We need to test different impact scenarios, develop more powerful and efficient propulsion systems, and improve our ability to simulate energy transfer in complex materials. The DART mission was a fantastic first step, but it's like the Wright brothers' first flight compared to the jumbo jets we need for planetary defense. Every new calculation and every new test brings us a little closer to understanding how to harness these unimaginable forces for our protection. The journey is daunting, but the alternative, being powerless in the face of an incoming mountain, is not an option. We must continue to invest in the science and engineering that will one day give us the power to move mountains in the vacuum, ensuring that we can always keep our homes safe from harm. This relentless pursuit of knowledge and capability is what defines us as a species capable of overcoming even the most monumental obstacles. The energy scale might be colossal, but so is our determination to survive and thrive. Let's keep pushing the boundaries, because the next time we need to move a mountain, we want to be ready. The challenge is immense, but with each breakthrough, we prove that no problem is too big for humanity to solve when we put our minds to it. The void of space may be vast and empty, but our resolve to fill it with our ingenuity is even greater. This is the promise of planetary defense, not just to avoid catastrophe, but to actively shape our destiny in the cosmos. And that is a goal worth every ounce of energy we can muster. The undeniable truth we must confront after discussing the immense energy requirements is that we can never be 100% certain our planetary defense system will work until the day we actually need it to save the world. This is the terrifying paradox of testing. We cannot ethically or practically run a full-scale, real-world drill on an asteroid that is genuinely headed for Earth. Our testing is therefore necessarily limited, conducted on safe, pre-selected targets that do not pose any threat, and while these tests are incredibly valuable, they can never fully replicate the immense pressure and unique conditions of a true planetary emergency. Think about the DART mission again. It was a magnificent achievement, a historic success that proved we can autonomously navigate to and impact a small celestial body. But it was, by design, a controlled experiment. The target was a moonlet in a stable, well-understood orbit around a larger asteroid. Scientists knew its size, its approximate mass, and its orbit with great precision long before the spacecraft was even built. The team had years to plan the impact, calculate the expected outcome, and monitor the results without the sword of Damocles hanging over their heads. There was no global panic, no political pressure, no countdown to potential annihilation. The stress and urgency of a real scenario were completely absent. In a real threat situation, everything would be different. The asteroid would be on a direct collision course, discovered perhaps with less warning time than we would like. Its properties, its exact mass, density, and internal structure might be largely unknown, estimated from remote observations with significant margins of error. The international decision-making process would be fraught with tension and diplomacy, potentially causing delays. The launch would happen under a global spotlight, with the eyes of the world and the weight of human civilization on the shoulders of everyone involved. This kind of pressure cannot be simulated in a test. The psychological factor alone is a variable that no software can model. Furthermore, every asteroid is unique. The DART mission taught us how a particular small moonlet, likely a rubble pile, responds to a kinetic impact. But the next threatening asteroid could be a solid monolith of iron and nickel. The one after that could be a fast-spinning, porous object with a completely different reaction to an impact or a nearby nuclear detonation. We cannot test our deflection methods on every type of asteroid in the solar system. We have to extrapolate from a very limited set of data points, and extrapolation is always risky. The laws of physics are the same everywhere, but how those laws manifest in the complex, heterogeneous structure of a specific asteroid is unpredictable. We rely heavily on complex computer simulations to model these interactions. We input what we know about an asteroid's suspected composition and our proposed deflection method, and the simulation predicts the outcome. These simulations are powerful, but they are only as good as the data we feed them. If we are wrong about the asteroid's internal strength or porosity, the simulation will be wrong. The model might show a successful deflection when in reality, the asteroid would fragment or absorb the impact inefficiently, without a way to validate these models against a real, threatening target. We are always operating with a degree of uncertainty. This is the practice is not the game problem. A football team can run drills all day, but that cannot perfectly prepare them for the chaos and unpredictability of a real championship match. We are practicing our planetary defense plays in a controlled scrimmage, but we will not know if our team can perform under the real pressure of a Super Bowl for the fate of humanity until it happens. The political and ethical constraints on testing are also immense. For instance, testing a nuclear deflection method, even a small-scale one, is currently impossible due to international treaties. Any proposal to detonate a nuclear device in space, even for a test, would trigger a global geopolitical crisis. This means the most powerful tool in our theoretical arsenal remains entirely untested in the environment where it would be used. We have computer models of how a standoff nuclear burst might work, but we have no empirical data. This is a staggering gamble to take when considering a last resort option. So, what can we do? We must pursue a rigorous program of incremental testing. Every mission to an asteroid, whether for science or for defense, provides more data. Missions like OSIRIS-REx and Hayabusa 2, which collected samples from asteroids, gave us invaluable information about surface composition and cohesion. We need more of these characterization missions to different types of asteroids to build a better library of their properties. We also need to conduct more deflection tests, but on a graduated scale. The next step might be a DART-like mission against a smaller dot, solid asteroid to see how the response differs from a rubble pile. After that, we might test a gravity tractor concept on a very small, harmless near-Earth object. We can also use analog experiments on Earth, such as using powerful lasers to simulate the effects of a standoff nuclear blast on surrogate asteroid materials. Though the low-gravity, vacuum environment of space is impossible to fully replicate. International tabletop exercises, where scientists and policymakers role-play a response to a fictional asteroid threat, are also crucial for testing our decision-making protocols under simulated pressure. While these steps will not eliminate the fundamental uncertainty, they will reduce it. They will build confidence, refine our models, and create a body of knowledge that makes us less reliant on guesswork. The goal is to shrink the zone of the unknown as much as possible, so that if we ever face a real asteroid, our predictions are based on a wide range of experimental data rather than a single data point. The sobering reality is that we are building a system we hope we never have to use, and we will never have the luxury of a full-scale dress rehearsal. Our first real-world test will be for all the marbles. This is a unique and profound responsibility. It means that our preparation must be exceptionally thorough, our technology must be exceptionally robust, and our international coordination must be exceptionally seamless. We are essentially placing a bet on our own ingenuity and preparedness, a bet with the highest possible stakes. This ultimate uncertainty should not paralyze us, but it should motivate us to be as prepared as humanly possible. We must test everything we can, within the limits of ethics and practicality. And for the things we cannot test, we must over-engineer our solutions and build in redundancies. The future of our civilization may one day depend on a system that has only ever been tested in simulations and limited experiments. Let's make sure those tests are as comprehensive and realistic as we can possibly make them. The work we do now in testing and validation is the down payment on that confidence. A confidence we will desperately need if we ever see a mountain in the sky with our name on it. This is the final, humbling challenge of planetary defense, accepting that we can never be completely sure, but moving forward with courage and determination anyway, doing everything in our power to be ready for that day. It is a testament to our spirit that we are even attempting this, and it is a burden we must bear with the utmost seriousness. The quest for knowledge continues, and with every test, we replace a little more uncertainty with understanding, building a safer future for generations to come. But just as we grapple with the inherent uncertainty of testing our defences against known solar system objects, we must now confront an even more elusive and unpredictable category of threat: interstellar asteroids. These are not native to our solar system. They are visitors from other star systems, passing through our cosmic neighbourhood at incredible speeds and from completely random directions. The discovery of Oumuamua in 2017 and Comet Borisov in 2019 was a monumental wake-up call, proving that such objects are not theoretical curiosities but real phenomena that we must now factor into our planetary defence equations. These interstellar interlopers represent a fundamentally different kind of challenge because they operate outside the rules we have come to understand for objects born in our own solar system. Their very nature makes them the definition of an unknown unknown, a threat that can appear with little to no warning, demanding a response system that is far more agile and broadly focused than anything we have today. The first and most daunting problem with interstellar asteroids is their speed. Objects within our solar system, like near-Earth asteroids, have orbits and velocities that are largely governed by the Sun's gravity, allowing us to predict their paths with some accuracy over long time frames. But an interstellar object is like a bullet fired from a distant gun. It enters our system at tremendous velocities, often tens of kilometers per second relative to the Sun. This means that even if we detect one, it might cross the entire inner solar system in a matter of months or even weeks, leaving us with a painfully short window to assess the threat and mount any kind of response. The time from detection to potential impact could be so compressed that our preferred method of gentle, early deflection becomes impossible, forcing us to consider high risk, last-ditch options like nuclear devices, with all their associated perils. Compounding the speed issue is the direction of their approach, Our current detection networks, both ground-based and space-based, are optimized to find objects moving along the ecliptic plane, which is the flat disk where most planets and asteroids in our solar system orbit. This makes sense because the vast majority of threats we have worried about come from this plane. But an interstellar object can come from any direction, including from high above or below this plane, from the galactic north or south, where our telescopes have historically spent less time looking. This is like having a security system that monitors the front and back doors of your house but ignores the windows and the roof. An interstellar asteroid could slip through these observational gaps, remaining undetected until it is already very close, dramatically reducing our reaction time. The sheer unpredictability of their origins and paths means we cannot rely on the long-term orbital tracking that we use for resident asteroids. Once an interstellar object is spotted, calculating its trajectory is a race against time. Their high speeds and hyperbolic orbits, paths that are not bound to the Sun, mean that small errors in initial observations lead to huge uncertainties in predicting where they will be just days or weeks later. This makes it extremely difficult to determine if they are on a collision course with Earth until they are almost upon us. The psychological impact of such a discovery would be profound. The realization that a threat could emerge from the depths of interstellar space, completely unforeseen, would challenge our sense of security and highlight the fragility of our planetary defense preparations. Moreover, the physical nature of these objects is a mystery. We know very little about their composition or structure. Are they solid rock, piles of rubble, or mostly ice-like comets? The limited data from Oumuamua suggested it had an unusual, elongated shape and showed non-gravitational acceleration, meaning something other than gravity was affecting its motion, possibly outgassing like a comet. Though no coma was visible, this unpredictability in behavior complicates any deflection plan. If we do not know what it is made of, how can we know how to push it? A kinetic impactor might work on one type, but could shatter another, creating a swarm of debris. A gravity tractor would require more time than we are likely to have. The nuclear option becomes even more of a gamble without understanding the target's internal strength. The detection challenge is further exacerbated by their potentially small size and dark surfaces. Many might be similar to dark, carbonaceous asteroids in our own system, reflecting very little light and thus being incredibly hard to spot until they are relatively close. Our current surveys are getting better, but they are still not comprehensive enough to scan the entire sky with the sensitivity and frequency needed to catch these fast-moving, faint objects with sufficient lead time. Projects like the Vera-C, Rubin Observatory will improve our all-sky coverage, but dedicated space-based telescopes with wide fields of view might be necessary to provide the constant vigilance required. The transient nature of these visits also means we have limited opportunities to study them. Unlike asteroids in our solar system that return periodically, an interstellar object like Oumuamua passes through once and is gone forever, making it impossible to conduct follow-up missions unless we have the capability to launch incredibly fast interceptors on short notice. This underscores the need for rapid response launch capabilities and pre-positioned assets that could be directed toward a newly discovered interstellar threat quickly. The existence of interstellar asteroids forces us to broaden our definition of planetary defense. It is no longer enough to catalogue and monitor the known objects in our solar system. We must now consider the entire celestial sphere as a potential source of danger. This requires a shift in strategy and investment. We need to enhance our sky survey telescopes to operate in all directions, not just along the ecliptic. We should invest in new technologies that can detect objects based on their heat signatures or other properties, rather than relying solely on reflected sunlight. International cooperation becomes even more critical, as a global network of observatories can provide continuous coverage of the entire sky, reducing the chances of a surprise from an unexpected direction. Additionally, we need to develop and practice response protocols for short warning scenarios. What do we do if we detect an object with a potential impact trajectory only a year or 6 months out? Our current systems are built on the assumption of decades of warning, but interstellar objects shatter that assumption. This might involve having deflection spacecraft, perhaps kinetic impactors or even nuclear devices, pre-built and ready for launch, with international agreements in place for their use in an emergency. The political and ethical challenges we have discussed earlier would be amplified in such a high-pressure, short time-frame situation. Decision-making would need to be streamlined, yet still involve global consensus to avoid unilateral actions that could be misinterpreted or lead to conflict. Public communication would be a nightmare. How do you inform the world about a threat that could be months away without causing mass panic? The cry wolf effect we talked about becomes even more dangerous here, as a false alarm could destroy trust precisely when it is needed most. In the grand scheme, interstellar asteroids remind us that our solar system is not an isolated island. We are part of a dynamic galaxy where objects are constantly moving between stars. While the probability of an impact from an interstellar object is likely even lower than from a local asteroid, the consequences would be just as severe, and the unpredictability makes them a unique and sobering challenge. They represent the ultimate test of our vigilance and adaptability. Our planetary defense efforts must evolve to account for these wild cards from the galactic deck by expanding our detection networks, investing in rapid response technologies, and fostering unprecedented international collaboration. We can hope to meet this challenge. The journey to secure Earth is never ending, and each new discovery, like that of Oumuamua, adds a layer of complexity that we must diligently address. Let us take this lesson to heart and ensure that our shield is not only strong but also wide, capable of protecting us from dangers both within and beyond our solar system. The cosmos is vast and full of surprises, but with perseverance and unity, we can strive to be ready for whatever comes our way. The terrifying reality we must now face, after considering all these technological and detection hurdles, is that even if we had a perfectly engineered deflection spacecraft ready on the launch pad, we currently have no agreed-upon global protocol for who should give the order to launch it. This is the ultimate political and logistical nightmare. Who gets to press the button? In a crisis scenario, with a confirmed asteroid on a collision course, the world would look for a leader, a command structure, a clear chain of responsibility, and it would find only a vacuum of authority and a tangle of diplomatic red tape. There is no existing international body with the legal or political mandate to authorize an action that could alter the shared environment of space for every nation on Earth. This decision-making paralysis could prove to be our undoing, wasting precious time while the threat draws nearer. The most obvious candidate for this authority would be the United Nations Security Council, but its structure, with the veto power held by 5 permanent members, is a recipe for potential disaster. Imagine a scenario where a deflection plan is proposed, but one permanent member vetoes it. The reasons could be myriad and frustratingly mundane from a cosmic perspective. Ongoing terrestrial trade disputes, political posturing, a desire to extract concessions, or simple distrust of the data provided by other nations. The world would be held hostage to earthly politics while a celestial object heads our way. The veto power, designed to prevent war, could ironically prevent a mission to save the world from a natural disaster. Alternatively, perhaps the authority should rest with a new, specialized international body, something like a planetary defense coordination organization governed by a council of scientists and engineers. But this immediately raises difficult questions about representation. Is it one nation, one vote? This would give small nations with minimal space capabilities an equal say to major space powers, which those powers would likely never accept. Would it be weighted by technological or financial contribution? This would cement the authority of a few wealthy nations, raising fears of a technocratic oligarchy making decisions that affect the entire globe. How would this body be formed? And who would appoint its members? The negotiations to create such an entity would be long and fraught, and we simply may not have that time. The question of who physically executes the mission is equally contentious. The actual launch of a deflection spacecraft would almost certainly be carried out by a specific nation or coalition, like the United States, Russia, Timor, China, or a European consortium. Would that nation be willing to cede command and control of its rockets and its spacecraft to an international committee? Would its military, which often oversees such launches, accept orders from an external entity? Conversely, would the rest of the world be comfortable with a single nation possessing and controlling the means to literally change the sky? This concentrates an immense and terrifying power in very few hands. The nation controlling the deflection could be accused of using the crisis to test new space weapons or to demonstrate its technological superiority for geopolitical gain. Even if their intentions are pure, the perception of ulterior motives could undermine global unity and trust at the most critical moment. The legal framework is another minefield. The Outer Space Treaty of 1967 establishes that states are responsible for their national activities in space, but it does not provide a clear protocol for a collective defensive action that alters a celestial body. If a deflection attempt goes wrong, for example, it fragments the asteroid and a piece strikes another country or damages another nation's satellites, who is liable? The launching nation, the international body that authorized it. The current legal structures are completely inadequate for assigning blame and liability in such an unprecedented event. This lack of a clear protocol creates a high risk of analysis paralysis, where nations debate and deliberate while the window for action slowly closes. The need for absolute certainty would be pitted against the relentless ticking of the cosmic clock. Scientists might insist on more data to refine the trajectory, while diplomats argue over the wording of a resolution. Meanwhile, the asteroid gets closer, and the energy required to deflect it grows exponentially. A decision that could have been made with a gentle nudge years in advance might, after months of debate, require a violent and risky nuclear option. The decision is further complicated by the inherent uncertainty in asteroid trajectory predictions. Early calculations always have a margin of error. An asteroid might have a 1% chance of impact initially. At what probability threshold does the world decide to act? Is it 10%, 50%, 99%? Reaching a global consensus on this risk threshold is itself a monumental challenge. Some nations might be willing to act on a lower probability, while others, perhaps those facing the direct economic burden of the mission, would demand near certainty. This problem is not just theoretical. We have seen smaller versions of it with global pandemics and climate change, where coordinated international action is often stalled by national self-interest and disputes over burden sharing. But with an asteroid, the timeline is compressed, and the consequence of inaction is immediate and catastrophic. So, what is the solution? We cannot wait for a crisis to force us to figure this out. We need to establish these protocols now, through painstaking international diplomacy. This means starting a global conversation, facilitated by the United Nations Committee on the Peaceful Uses of Outer Space, to draft a new treaty or a set of agreed-upon procedures for planetary defence. This treaty would need to address several key points. First, it must define a clear chain of command. It could, for example, grant ultimate authority to the UN Security Council, but with a special provision that a veto on a planetary defence mission can be overridden by a supermajority vote in the General Assembly in a time of crisis. Second, it must establish a transparent and trusted international scientific body, perhaps under the auspices of the International Astronomical Union, whose sole job is to assess and communicate the threat level to the decision-making body. Their data and models must be open to all to build trust. Third, the treaty must predefine the thresholds for action. What probability of impact, combined with what estimated size of the object, triggers what level of response. Having these thresholds agreed upon in advance removes one layer of debate during a crisis. Fourth, it must clarify liability, creating a fund or an insurance mechanism to handle damages from any unintended consequences of a deflection attempt. This is a daunting diplomatic task, but it is essential. We also need to practice international asteroid defense drills, simulating the entire process from detection to decision-making to launch authorization, are crucial. These exercises would reveal the friction points in our diplomatic and political systems and allow us to smooth them out before a real asteroid does. The creation of a global decision-making protocol is the final, indispensable piece of the planetary defense puzzle. Without it, our brilliant engineers, our powerful rockets, and our sensitive telescopes are just tools without a hand to wield them. We can have the capability to save the world, but without the wisdom and unity to decide to use it, that capability is meaningless. This is the ultimate test of our global governance. It forces us to ask whether we are still a collection of squabbling tribes or if we have evolved into a planetary civilization capable of collective action for the common good. The asteroids are coming. It is only a matter of time. Let us ensure that when one finally has our name on it, we have already decided who gets to speak for Earth. The time to build this protocol is now. While the sky is still clear, our survival may one day depend not on a technological breakthrough, but on a diplomatic one. So, we have finally navigated the diplomatic minefield and established a global protocol for who gets to press the button. But that hard-won agreement is merely the starting pistol for a race that has no finish line. A commitment that must be upheld not for years, but for centuries, even millennia. Building the shield is one thing. Maintaining its sharp edge and keen sight across generations is an entirely different, and perhaps more difficult, challenge. This is the long-term legacy problem. And it forces us to think on timescales that are alien to our modern, short-term focused societies. A planetary defense system is not a project with a completion date. It is a permanent civilizational endeavor, a new organ of our global body that must be nurtured, funded, and updated forever. The first and most obvious challenge is technological obsolescence. The telescopes, computers, and spacecraft we build today will be antiquated in 50 years and utterly useless in 100. The software running our detection algorithms will become incompatible. The materials in our satellites will degrade, and our understanding of asteroid threats will evolve. This means we cannot simply build a system and walk away. We need a permanent, rolling program of research and development, constantly designing and launching next-generation telescopes with better sensors, building more efficient and powerful deflection spacecraft, and developing more accurate simulation software. This requires a continuous pipeline of funding, innovation, and engineering talent, generation after generation. It means that the budgets we fight for today must become a permanent, non-negotiable line item in global expenditures, as routine as funding a military or a healthcare system, but with the goal of protecting against a threat that might not materialize for 1,000 years. The financial commitment is staggering to contemplate. It is not a one-time cost of trillions, but an eternal drain on the global economy, convincing taxpayers and governments to perpetually fund a system that has never been used in a real crisis, for a threat that feels increasingly abstract with each passing peaceful year, is a psychological and political battle that will be fought over and over again. The moment a generation arises that did not witness the founding of the system or the near misses that inspired it, is the moment the funding is most at risk. They will ask, why are we spending so much on something that never happens? This is where education becomes critical. The knowledge of the threat, the memory of past impacts like the one that wiped out the dinosaurs, and the understanding of the system's purpose must be woven into the very fabric of our culture, taught in schools and reflected in our stories, so that each new generation feels a personal responsibility to be guardians. The knowledge transfer itself is a huge vulnerability. The specialized skills needed to operate and improve the system, orbital mechanics, spacecraft engineering, nuclear physics for last resort options, are not easily preserved. We have seen how quickly knowledge can be lost. Consider the centuries it took to rediscover the concrete formulas of the Romans, if a period of global instability, a dark age, or even a prolonged war were to interrupt the continuous operation and training for the planetary defense system, the institutional knowledge could evaporate. We would be left with crumbling hardware and no one who remembers how to fix it or why it was built. This necessitates not just training programs, but the creation of a resilient, decentralized global guild of planetary defense experts, with redundant centers of learning and data storage immune to regional conflicts. The infrastructure itself is vulnerable to neglect. The network of ground-based telescopes needs constant maintenance. The space-based assets have limited lifespans and must be replaced before they fail. The launch facilities must be kept in a state of readiness. Any significant gap in monitoring, even for a few years, could allow a new, previously unknown asteroid to approach undetected until it is too late. The system is a chain, and every link must be held taut forever. Furthermore, the threat landscape is not static. Our solar system is dynamic. New asteroids are constantly being nudged into Earth-crossing orbits by gravitational interactions with Jupiter. Long-period comets, which spend most of their time in the outer reaches of the solar system, can come screaming into the inner system with very little warning. Our shield must be adaptable enough to counter these new and unpredictable threats. This means our detection networks must constantly expand and improve, and our deflection technologies must be versatile. A method that works for a slow-moving, rocky asteroid might be useless against a fast, icy comet. The political and social fabric required to sustain this effort is fragile. The international cooperation we painstakingly built could be shattered by a major war or a deep economic depression. If nations turn inward and cease sharing data or funding the joint effort, the system would fail. The shield is only as strong as the peace and prosperity that underpins it. This long-term perspective also introduces ethical questions for which we have no answers. Are we morally obligated to maintain this system for our descendants 10,000 years from now? What if future societies develop different values and decide the cost is not worth it? Do we have the right to bind them to this eternal vigilance? There are no easy answers, but the consequence of dropping our guard is the potential end of human civilization. The maintenance of the shield is therefore a test of our species' maturity. It is a commitment to think and act not in electoral cycles or quarterly reports, but in geological time. It is a promise we make to the future, a promise that we will keep watch so that they may live. This is the ultimate legacy of our generation if we choose to accept it. We would be the ones who looked into the cosmos, saw a danger, and decided not just to deflect it once, but to establish a permanent guard against it. The work is never done. There is no victory parade, only the quiet satisfaction of a job that must continue forever. It is a humble, relentless, and noble task. Let us ensure that we build not just the technology, but the enduring institutions, the cultural memory, and the unbreakable global will to maintain it. The shield is not a monument to our fear, but a testament to our hope for a forever future. And that is a legacy worth building, maintaining, and passing on, for as long as humanity calls Earth home. The journey does not end with a launch or a treaty. It begins with a commitment echoed through the ages, a whisper from the past to the future saying, "We are still here, we are still watching, and we are still protecting our home." This is the price of our survival, and it is a price we must be willing to pay, today, tomorrow, and for all the tomorrows to come. The stars may hold infinite wonders, but our first duty is to the pale blue dot that gave us life, and ensuring its story continues is the greatest story we will ever tell. So, as we look to the future, let us do so with the long view, understanding that the true measure of our success won't be in the asteroids we deflect next year, but in the vigilance we maintain for the next 1,000 years. This is our pact with time itself, and we must honour it with every resource we have. The shield is more than metal and code. It is the embodiment of our collective will to endure, and that is something we must never let grow dull. The challenge is eternal, but so is the potential of the human spirit to rise to it.